Hey everyone, today's journey plunges you into the heart of a cosmic colossus as we explore what it would be like if you fell into a black hole, diving headfirst into the unknown. Before you settle in, please like and subscribe. Your support makes these mind-bending voyages possible. Let us know where you're tuning in from and what time it is in your corner of the universe. Now dim the lights, wrap yourself in something warm, and let the soft crackle of a fire or the gentle hum of your night lamp guide your mind toward calm. Prepare to drift into rest as we cross the event horizon. Feel the pull of spaghettification and wonder what lies beyond the point of no return. Imagine yourself drifting through the silence of deep space. The infinite black stretches in all directions, punctuated only by the distant diamonds of starlight. You're alone out here, wrapped in the perfect void, when something catches your eye. A patch of nothingness darker than the surrounding darkness. A perfect circle of absence where stars should be. You've just spotted it. A black hole, the cosmic drain where matter goes to be forgotten. And somehow, against all survival instincts, you're moving toward it. Welcome to the ultimate one-way journey. I'm your guide through what will prove to be the most comprehensive tour of reality's most forbidden destination. No living being has ever reported back from beyond a black hole's embrace, which makes this a unique documentary indeed. What you're about to experience is simultaneously the most extreme physics lecture and the most terrifying horror story in the universe. Let's establish some basics. The black hole you're approaching isn't just dark matter or a very dense star. It's a region where gravity has completely overwhelmed all other forces, creating a puncture in the fabric of space-time itself. Specifically, you're heading toward a stellar mass black hole, roughly 10 times more massive than your sun. Small by cosmic standards, but more than enough to demonstrate what happens when physics reaches its breaking point. For now, you're still 20 million light-years away. Safe, observing, but not for long. Your spacecraft, let's say it's the size of a modest apartment, begins its approach. The engines fire, and you commit to the most ill-advised scientific expedition in human history. The stars around you appear normal at first. The black hole itself is still just a dark smudge against the cosmic backdrop. But as you cross the distance from 20 million to merely 20,000 light-years, the first hints of something extraordinary become apparent. The star field behind the black hole begins to behave oddly. Stars that should be blocked by the black hole's profile seem to bend around it, appearing as perfect rings of light. This is gravitational lensing, the bending of light by extreme gravity. The black hole is so massive that it curves space-time around itself, redirecting light like a cosmic funhouse mirror. Stars that should be hidden become visible, warped into concentric circles around the dark center. You accelerate, 10,000 light-years now. The gravitational lensing intensifies. Stars begin smearing around the black hole's silhouette, stretching into thin arcs of light. It's as if someone took the cosmic canvas and pulled at it from the center, dragging starlight into bizarre new patterns that would make even the most experimental artist question their sanity. The effect is beautiful in a deeply unsettling way. You're witnessing the distortion of one of the universe's most fundamental structures, the path that light travels. Light, which normally moves in straight lines, is being forced to follow the curved geometry that the black hole has stamped onto space-time itself. At 1,000 light-years, your sensors detect the first gravitational waves emanating from the black hole. These ripples in space-time wash over your ship, barely perceptible but present nonetheless. Like the first tiny waves lapping at your feet before a tsunami, they herald the immense gravitational forces awaiting you. 500 light-years. The black hole no longer appears as a simple dark circle. It's developed a complex structure to your eyes, the perfect blackness of the event horizon, which means the point of no return where not even light can escape, sits at the center. Around it, a strange distortion warps the star field behind it. Light from stars directly behind the black hole forms what astronomers call an Einstein ring, a perfect circle of light surrounding the darkness. Stars that are slightly offset create incomplete arcs and multiple images, as if reflected in some cosmic kaleidoscope. You check your instruments. 100 light-years away now. The black hole dominates your forward view. At this distance, another effect becomes noticeable. The stars around the black hole appear to be moving at accelerated speeds. This isn't an illusion. The black hole's gravity well is so deep that it actually alters the flow of time. You're witnessing a preview of the temporal horrors awaiting you, as time itself begins to stretch and compress in your field of view. At 10 light-years, the gravitational influence becomes more than just visual. Your ship's artificial gravity struggles to compensate for the tidal forces, the difference in gravitational pull between the side of your ship facing the black hole and the side facing away. It's subtle at this distance, but instruments don't lie. The black hole is already reaching out to you, probing your physical structure with invisible fingers of warped space-time. 1 light-year away, the black hole now dominates not just your view but your reality. The event horizon appears much larger than it physically should, another trick of extreme gravity. Light that skims close to the black hole without falling in can orbit it several times before escaping to reach your eyes, creating complex layers of images. Stars that should appear once now have twins, triplets, or entire families of identical copies arranged in patterns that make your visual cortex throb with confusion. You're close enough now that relativistic effects begin distorting colors. Stars ahead of you, whose light has to climb out of the black hole's gravitational well before reaching you, appear redder than they should. Their light waves are stretched by gravity, shifting toward the red end of the spectrum. This is gravitational redshift, the visible evidence that gravity is stretching the fabric of reality around you. At 0.1 light-years, roughly 600 billion miles, the black hole's immense gravity begins affecting your perception more directly. The black hole appears to grow faster than your approach would suggest, another relativistic illusion. The event horizon seems to reach out for you, though in reality, it's your perception of space that's warping. The visual distortions become more pronounced. The universe behind the black hole is no longer recognizable as normal space. Stars stretch into thin lines, then curve into spirals that wrap around the black hole's silhouette. The sky becomes a twisted mural of light, a cosmic Edvard Munch painting with the black hole as its silent scream. You continue your approach. At a distance of 10 billion miles, roughly the distance from your sun to Saturn, the black hole's gravitational field begins to affect your perception of time as well as space. Your ship's atomic clocks, synchronized with Earth's, begin to drift. Time is flowing more slowly for you than for the rest of the universe. It's barely noticeable at first, milliseconds of difference, but it's the first hint of the temporal abyss awaiting you. 1 billion miles now, the black hole's event horizon, that perfect boundary of no return, occupies nearly half your field of view. But describing what you're seeing becomes increasingly difficult, because the black hole doesn't just distort the light from objects behind it, it distorts your very perception of geometry. The event horizon doesn't look like a sphere anymore. It appears flattened, distended, as if space itself is being stretched like taffy. This is no illusion. It's the actual warping of space-time made visible. The normally straight paths of light rays are being bent into curves, some gentle and some extreme, creating a visual environment that no human evolved to comprehend. At 100 million miles, another effect becomes apparent. The black hole appears to rotate, dragging the fabric of space around it like a spoon swirling in honey. This is frame dragging, where a massive rotating object literally pulls space-time along with it as it spins. Stars that should move in straight lines appear to spiral around the black hole, following the twisted contours of space itself. 10 million miles. The tidal forces are now strong enough that your ship's systems begin issuing warnings. The gravitational pull on the front of your vessel is measurably stronger than on the back, creating a stretching effect. It's mild at this distance, nothing structural will fail, but it's a foretaste of the anatomical rearrangements awaiting your body later in this journey. You can no longer see the entire event horizon at once. It's too vast, too close, filling more than your field of view. Instead, what you see is a bizarre optical illusion, a dark sphere that somehow appears both convex and concave simultaneously, as if your visual cortex can't decide whether you're looking at a hole or a ball. The mathematical precision of the event horizon's curvature creates visual paradoxes that make your mind reel. 1 million miles, the universe behind you appears relatively normal, but the universe ahead has been transformed into an alien landscape of light and geometry. Stars no longer look like points but have stretched into arcs and loops, some circling the black hole multiple times before continuing on their way. What you're seeing is the actual path that light takes through severely warped space-time, not an artistic representation, but the genuine structure of reality under extreme conditions. The gravitational redshift has become extreme. Stars whose light passes near the black hole before reaching you have shifted so far into the red that they've become invisible to human eyes, detectable only by instruments. Some have shifted all the way into radio frequencies, visible light transformed into radio waves by the sheer force of gravity. At 100,000 miles, less than half the distance from Earth to its moon, time dilation becomes significant enough that your ship's computers must constantly recalibrate. Each minute for you is now several minutes for the outside universe. Your communication signals to any hypothetical mission control would arrive noticeably delayed and frequency shifted, not just from the travel time of light but from the time differential itself. The event horizon now appears as a vast black wall ahead of you, curving away at the edges of your vision. Its perfect blackness is disorienting. Not just dark, but an absence of light so complete that your eyes struggle to focus on it. Against this backdrop, the last visible light from stars performs an elaborate dance, tracing the invisible contours of warped space like quantum fireflies following magnetic field lines. 10,000 miles. The tidal forces are strong enough now that you can feel them physically. The gravitational pull on your feet is measurably stronger than on your head, creating a subtle stretching sensation. It's not painful yet, more like the feeling of a gentle acceleration, but it's a reminder that the black hole is now interacting with your body directly, probing your physical structure with invisible fingers of gravity. The visual distortions have reached hallucinatory levels. Space itself appears to flow around the black hole like a liquid, carrying starlight with it in swirling currents. Light rays that pass near the event horizon can orbit the black hole several times before escaping, creating multiple ghost images of each star, some showing the star as it looked years before others. You're not just seeing distorted space, you're seeing distorted time made visible. 1,000 miles. The event horizon looms like a black mountain, encompassing your entire forward view. The tidal forces are now uncomfortable, a persistent pulling sensation as the black hole's gravity attempts to stretch you vertically. Your ship's artificial gravity struggles to compensate, creating pockets of stronger and weaker gravity throughout the vessel. The time dilation has become severe. Each second for you is now minutes for the distant universe. If you could somehow observe Earth, you would see it moving in fast forward, like watching a time-lapse video of civilization evolving. But your focus is ahead, on the perfect darkness that promises to swallow not just your body but the very information that constitutes your existence. At 500 miles you encounter the photon sphere, a special region where light can orbit the black hole in perfect circles. This creates the most bizarre visual effect yet. You can see the back of your own head. Light from behind you can orbit the black hole completely, returning to your eyes from the front. The universe becomes a house of mirrors, with multiple images of the same stars appearing in different directions, some moving forwards in time, some backwards. 100 miles from the event horizon, the tidal forces have become seriously uncomfortable. You feel as if giant hands are pulling your head and feet in opposite directions. The internal structure of your ship begins to creak and groan under these differential forces. Structural warnings flash across your screens. 50 miles. The event horizon is so close that it no longer appears curved but instead like a black wall of perfect darkness extending infinitely in all directions. The distortion of space-time is so extreme that conventional descriptions of geometry fail entirely. Your instruments struggle to make sense of the measurements they're taking, as if reality itself is becoming fluid, refusing to be pinned down by mere numbers. 25 miles. The tidal forces are now actively painful. Your spine elongates slightly, joints stretching uncomfortably. Looking down at your hands, you notice your fingers appear longer and thinner than normal. This isn't an illusion. It's the beginning of the process astrophysicists casually call spaghettification, the vertical stretching and horizontal compression of matter in extreme gravitational gradients. 10 miles from the event horizon, every atom in your body feels the differential pull of gravity now. Your feet are being pulled toward the black hole significantly harder than your head, creating a stretching sensation that makes you feel as if you're on a medieval torture rack. Your ship's structure begins to fail, metal beams bending and twisting under forces they were never designed to withstand. 5 miles. The pain is intense now. Your body is being stretched noticeably, painfully. Looking down at yourself, you see your torso elongating, your limbs growing thinner as they're stretched vertically and compressed horizontally. Blood struggles to circulate against these tidal forces, creating pockets of pressure and vacuum within your cardiovascular system. 1 mile. The tidal forces have become genuinely destructive. Your ship's structural integrity fails completely, metal tearing and fragmenting around you. Your body undergoes catastrophic elongation, bones separating at joints, tissues stretching beyond their breaking points. The pain is beyond description, but mercifully brief as your nervous system itself is pulled apart. And yet, from a physics perspective, you haven't even reached the most interesting part of the journey. The event horizon still lies ahead, that perfect boundary between the knowable universe and whatever lies beyond. Your component atoms, now arranged in a thin stream rather than a human shape, continue their inexorable fall toward this cosmic point of no return. But what happens next? The actual crossing of the event horizon and everything beyond requires a deeper examination of the most extreme physics in the universe. Your body is no longer recognizable as human, having been transformed into an elongated stream of component particles by the tidal forces. These particles, however, continue their journey inward, about to experience the next phase of black hole torments, a process so bizarre that it makes the distortions you've witnessed so far seem mundane by comparison. As the atoms that once constituted your body approach the event horizon itself, they experience the ultimate distortion of reality. Space and time begin to exchange roles in a way that defies intuition but follows directly from Einstein's equations. The direction toward the black hole becomes less like a direction in space and more like a direction in time, forward, inexorable, impossible to resist. And as these particles cross that invisible boundary, they enter a domain where the known laws of physics begin to unravel, where quantum effects and gravitational extremes create conditions found nowhere else in the universe. But that's getting ahead of ourselves. Let's back up slightly, to examine in excruciating detail exactly how your body is transformed from a reasonably stable collection of atoms into a thin stream of elementary particles. Let's talk about spaghettification. Let's rewind slightly. You're still approximately 100 miles from the event horizon, the point of no return. Your ship is creaking under the strain of tidal forces, and you're experiencing the first uncomfortable sensations of gravitational stretching. This is where the real bodily horror begins, a process so grisly and yet so mathematically elegant that it deserves its own term: spaghettification. Spaghettification sounds almost comical, like something from a children's science program. The whimsical name belies the excruciating reality. It's what happens when an object, say a human body, experiences significantly stronger gravity at one end than the other. And in the extreme gravitational gradient near a black hole, that difference becomes literally tear-inducing. Let's break down exactly what's happening to your body at this moment. The black hole's gravity follows the inverse square law: double the distance, and the gravitational force decreases to 1/4. This means that the gravitational pull on your feet is noticeably stronger than on your head, even with just 6 feet of height difference. Near a black hole, this gradient becomes so extreme that it overwhelms the electromagnetic forces holding your atoms together. At 100 miles from the event horizon, you feel an intense stretching sensation. It begins subtly, a feeling like you're being pulled in opposite directions by invisible forces. Your height increases by fractions of an inch as your spine elongates slightly. It's uncomfortable, but not yet painful. Your organs shift inside your body cavity, pressing against each other in unfamiliar ways. As you continue your approach, now 75 miles from oblivion, the stretching intensifies. Your height has increased by several inches now. Looking down at your hands, you notice your fingers appear unnaturally long and thin. Blood struggles to circulate normally as vessels stretch and narrow. You begin to feel lightheaded as your cardiovascular system fights against the tidal forces. At 50 miles, the pain becomes difficult to ignore. Your joints begin to separate slightly, the synovial fluid between them stretching into thin films. Your muscle fibers elongate beyond their normal operating parameters, triggering intense cramping throughout your body. Your skin stretches taut, blood vessels visible beneath the surface, like rivers seen from space. 40 miles from the event horizon, and the structural integrity of your body begins to fail. The intervertebral discs in your spine, normally compressed by gravity, now stretch and bulge. The sensation is similar to the most extreme spinal decompression therapy, except instead of stopping at therapeutic limits, it continues relentlessly. Your height has increased by nearly a foot now, your body proportions distorted beyond recognition. At 30 miles, the tidal forces overpower the tensile strength of your tendons and ligaments. Joints begin to separate. Your shoulders dislocate first, the humerus pulling away from the glenoid cavity with an audible pop. Your hips follow, femurs distancing themselves from your pelvis. The pain is extraordinary, but there's a curious phenomenon at play. Your nerves themselves are being stretched and distorted, creating strange gaps and overlaps in your pain perception. Some areas feel nothing at all, while others experience hyperacusis of pain, magnifying even slight pressures into overwhelming agony. 25 miles from the event horizon, your body no longer remotely resembles a human form. Your torso has stretched to several times its normal length, with organs displaced and elongated within. Your digestive tract resembles a thin garden hose rather than its normal convoluted structure. Your brain, protected somewhat by the skull, nevertheless undergoes dramatic distortion as cerebrospinal fluid redistributes and neural connections stretch beyond their functional limits. The tidal forces aren't just stretching you vertically, they're simultaneously compressing you horizontally. Your body becomes thinner as well as longer, the circumference of your chest and abdomen reducing dramatically. This combination of vertical stretching and horizontal compression is what creates the spaghetti effect that gives this gruesome process its name. 20 miles from the event horizon, individual tissues begin to fail catastrophically. Skin tears along stress lines, unable to stretch any further. Blood vessels rupture, though the blood doesn't spray as it would under normal conditions. Instead, it forms elongated droplets that themselves undergo spaghettification. Your bones, despite being the strongest materials in your body, begin to separate at growth plates and stress points. The inside of your body becomes a grotesque anatomy lesson. Organs stretch into unrecognizable shapes, their functions completely disrupted. Your lungs, normally elastic and resilient, flatten into thin sheets, unable to exchange oxygen and carbon dioxide. Your heart, still valiantly attempting to pump, stretches into a tube-like structure, its chambers elongated to the point where normal contraction becomes impossible. 15 miles. The molecular structures within your body begin to experience the tidal forces directly. Collagen fibers, the structural proteins that give your tissues their strength, unwind and straighten. Cell membranes stretch and rupture, releasing their contents into the increasingly linear stream of material that was once your body. DNA strands, normally tightly coiled, extend to their full length and beyond, breaking at weakened points. At 10 miles from the event horizon, your body has been reduced to a thin stream of organic matter, stretched along the radial line toward the black hole. The complex arrangements of atoms that once formed your organs, tissues, and systems have been forcibly rearranged into a linear gradient. What was once a three-dimensional human being is now essentially one-dimensional, a line of component materials sorted by density. But the horror show doesn't end there. As this stream of ex-human material continues its fall toward the event horizon, the tidal forces grow even stronger. At 5 miles out, individual molecules begin to break apart. Chemical bonds, the electromagnetic attractions that hold atoms together in molecules, are overwhelmed by the gravitational gradient. Proteins unravel completely. Lipids separate into their component parts. The complex organic chemistry that enabled your existence simplifies into increasingly basic compounds. 3 miles from the event horizon, even atomic structures begin to feel the strain. Electron orbitals, normally spherical or elliptical clouds around atomic nuclei, distort into teardrop shapes, pointing toward and away from the black hole. Some electrons are stripped away entirely, creating a stream of ionized particles. 1 mile out, the atomic nuclei themselves begin to deform under the tidal forces. Protons and neutrons, pulled more strongly at one end than the other, stretch into oblong shapes. The strong nuclear force, the fundamental interaction that holds nuclei together, begins to battle against the gravitational gradient. At this distance, the matter stream that was once your body still contains the same atoms, but arranged in a fundamentally different way. The complex, information-rich structure that constituted you as a person has been completely erased, replaced by a simple radial organization based solely on the gravitational field. Half a mile from the event horizon, the tidal forces have now reduced what was once a human body to a stream of subatomic particles. Atomic nuclei have been torn apart, their protons and neutrons separated. These nucleons themselves are on the verge of breaking down into their constituent quarks, held together only by the strong nuclear force's resilience against the gravitational tidal forces. The pain, of course, ended long ago, not because the process became less destructive, but because the structures necessary for pain perception were among the first to be destroyed. Consciousness, that emergent phenomenon arising from the complex interactions of neurons, ceased when your brain was stretched beyond recognition. What continues to fall toward the black hole is merely matter that was once organized into your form. A quarter mile from the event horizon, the subatomic particles that once formed your atoms have been stretched into an even thinner stream. Quantum effects begin to play a significant role as these particles approach the event horizon. From an outside observer's perspective, time appears to slow drastically for these particles, an effect of the extreme gravitational time dilation near the event horizon. This is where we encounter one of the most profound paradoxes in black hole physics. From the perspective of a distant observer, this stream of particles never quite reaches the event horizon. Due to gravitational time dilation, time appears to slow asymptotically, with the final approach taking an infinite amount of external time. The particles appear to freeze at the horizon, gradually fading from view as their light undergoes extreme redshifting. But from the perspective of the particles themselves, if such a perspective could exist, the event horizon is crossed in a finite and actually quite brief amount of proper time. There's no membrane or barrier at the event horizon, no physical surface that marks the boundary. The particles continue their inward fall, oblivious to the fact that they've crossed a point of no return, that they've entered a region from which even light cannot escape. This dual perspective, the eternal freezing at the horizon from an outside view versus the uneventful crossing from the falling perspective, is not a contradiction but a consequence of how space and time themselves behave in extreme gravitational fields. It's a reminder that in the vicinity of a black hole, our intuitive notions of space and time break down completely. But let's back up just a bit. We've been discussing the fate of your body, as if it fell directly toward a static, non-rotating black hole. In reality, most black holes in the universe rotate, some at significant fractions of the speed of light. This rotation drags space-time around with it, creating additional effects that complicate the spaghettification process. In a rotating black hole technically called a Kerr black hole after the mathematician Roy Kerr who solved Einstein's equations for this case, the event horizon is no longer spherical but oblate, flattened at the poles and bulging at the equator. More importantly, there's an additional region outside the event horizon called the ergosphere, where space-time itself is dragged along with the black hole's rotation. If your fall took you through the ergosphere, you would find yourself irresistibly dragged in the direction of the black hole's rotation, even if you fired thrusters in the opposite direction. It's not that some force pushes you along, it's that space itself is moving, carrying you with it like a leaf caught in a whirlpool. This frame-dragging effect would add a rotational component to your spaghettification. Instead of being stretched simply along a radial line toward the center, your component particles would be stretched into a spiral pattern, twisted around the black hole as they fall. The resulting stream would resemble less a straight line of spaghetti, and more a corkscrew of cellular debris. Another complication we've overlooked: most real black holes don't exist in isolation, but are surrounded by accretion disks, swirling maelstroms of superheated gas and dust being gradually consumed by the black hole. If your fall took you through such an accretion disk, you would encounter temperatures of millions of degrees and radiation intense enough to dissociate your molecules long before gravitational tidal forces could do their work. In fact, for supermassive black holes, the behemoths lurking at the centers of galaxies with masses millions or billions of times that of the Sun, spaghettification might not be your primary concern. These black holes are so large that their gravitational gradients are actually less steep at the event horizon. You could potentially cross the event horizon of a supermassive black hole without experiencing catastrophic tidal forces. Of course, you'd still be doomed. Once inside the event horizon, all possible paths lead inexorably to the singularity at the center, but at least you'd remain intact long enough to contemplate your fate. For the stellar mass black hole we've been considering, however, spaghettification remains the dominant experience. The tidal forces are simply too extreme for any physical structure to withstand. From the complex organization of a human body to the fundamental particles that constitute matter, everything is reduced to a radial stream sorted by the gravitational field. There's a certain elegant horror to this process. The same fundamental force that shapes the largest structures in the universe, gravity, which forms galaxies and orchestrates the cosmic dance of celestial bodies, also dismantles the smallest structures when concentrated in a black hole. From the grandest to the most minute scales, gravity demonstrates its inexorable power. But there's another aspect of black hole physics that adds an additional layer of existential dread to your fall: time dilation. While your body is being stretched and dismantled by tidal forces, time itself is playing tricks that challenge our most fundamental assumptions about reality. As you approach the event horizon, time slows down dramatically compared to the outside universe, an effect that leads to some of the most mind-bending consequences in all of physics. For you, the fall toward the black hole might seem to take minutes or hours, but for a distant observer watching through some impossibly powerful telescope, your fall appears to slow asymptotically as you approach the event horizon. From their perspective, you never quite reach it, instead becoming frozen in time at the boundary, gradually redshifting into invisibility as the black hole's gravity stretches the wavelength of light to imperceptible lengths. This temporal distortion affects not just observations but the very nature of your experience. The universe outside accelerates from your perspective, stars wheeling across the sky at impossible speeds, galaxies evolving in what seems like moments. Billions of years might pass in the outside universe during what feels like minutes to you. This is not a perceptual illusion, but a fundamental feature of how space-time behaves in strong gravitational fields. Time genuinely flows differently near a black hole, a phenomenon that raises profound questions about the nature of reality and experience. When we say that time slows down, we don't mean that your subjective perception changes, we mean that time itself as a dimension of reality becomes stretched and distorted. And this brings us to one of the deepest paradoxes in black hole physics, the apparent contradiction between what different observers see happening at the event horizon. From the perspective of a distant observer, nothing ever crosses the horizon, instead becoming frozen there for eternity. From the perspective of the falling observer, the horizon is crossed without incident in a finite amount of proper time. This isn't a quirk of perception but a fundamental feature of general relativity. Different observers genuinely experience different realities depending on their state of motion and position in a gravitational field. Near a black hole, these differences become so extreme that they challenge our most basic intuitions about the nature of reality. As your component particles cross the event horizon, from their perspective, not from that of a distant observer, they enter a region where the rules change dramatically. Inside the horizon, the direction toward the singularity becomes time-like rather than space-like, meaning that avoiding the center becomes as impossible as avoiding the future. Just as you cannot help but move forward in time under normal circumstances, you cannot help but move toward the singularity once inside the event horizon. This transformation of space into time and time into space is perhaps the most profound aspect of black hole physics. It represents a fundamental reshaping of reality itself, a domain where the familiar guideposts by which we navigate the universe are rearranged into an alien configuration that defies intuition. And at the center awaits the singularity, a point of zero volume and infinite density, where our current understanding of physics breaks down completely. What happens to the information contained in your body, the specific arrangement of particles that constituted you as a unique individual, becomes one of the most profound questions in theoretical physics, the infamous black hole information paradox. But before we delve into those quantum mechanical depths, let's explore another aspect of your fall into the black hole, the bizarre temporal effects that make black holes not just spatial anomalies but temporal ones as well. The distortion of time near a black hole creates a situation where your brief journey becomes, from an outside perspective, an almost eternal tableau. Let's examine the nightmare of time dilation that awaits any matter falling into these cosmic traps. Time as you understand it on Earth is a relatively simple affair. Seconds tick by at a constant rate. The minute hand makes its steady circuit, the Earth rotates on its axis, and revolves around the Sun with reassuring predictability. The fundamental particles in your brain decay at standard rates, and the electrochemical signals that constitute your thoughts propagate at consistent speeds. All of this creates the illusion of universal time, a cosmic metronome keeping everything in the universe synchronized. But Einstein shattered this comforting illusion over a century ago. Time, he revealed, is relative. It flows differently depending on your velocity and your position in a gravitational field. These effects are minimal in your everyday life. Nanoseconds of difference when you climb a mountain or fly in an airplane, but near a black hole, time's malleability becomes a nightmare of stretched moments and compressed eternities. As you approach the black hole, still intact at roughly 1,000 miles from the event horizon, the first noticeable temporal effects begin. Your ship's atomic clocks, synchronized with Earth's, start to drift. The drift is subtle at first, seconds over hours, but it's the beginning of a temporal divergence that will quickly become extreme. At 500 miles, the time dilation becomes significant enough that if you could somehow maintain communication with Earth, you would notice a distinct lag. Your messages would arrive increasingly delayed, not just from the travel time of light, but from the time differential itself. Your voice would sound lower, your video feed would slow down, all evidence of time stretching like taffy between your ship and the distant Earth. At 200 miles from the event horizon, each minute you experience corresponds to several hours for distant observers. The universe outside appears to be running in fast forward. If you could still see Earth through your telescopes, you would witness days passing in minutes, seasons changing before your eyes. Generations would be born, live, and die during what feels to you like an afternoon nap. This is not a perceptual illusion. Time itself flows differently in your vicinity. The extreme curvature of space-time near the black hole literally stretches the temporal dimension, creating a genuine divergence between your experience of time and that of the outside universe. At 100 miles, the differential becomes even more extreme. Each second for you is now days for the outside universe. If you held a communication link with Earth, ignoring for the moment the extreme redshift that would make such communication nearly impossible, you would hear people speaking at impossibly high speeds, like a recording played back at thousands of times normal rate. Conversely, to observers on Earth, you would appear to move in extreme slow motion. A wave of your hand would take weeks to complete from their perspective. Your speech would be so deep and slow as to be inaudible, stretched from kilohertz to millihertz. At 50 miles from the event horizon, the time dilation reaches truly mind-bending proportions. Each heartbeat you experience corresponds to years passing in the outside universe. If Earth still exists, and given the temporal scales involved, this is increasingly unlikely. Civilizations would rise and fall between your breaths. Species would evolve and go extinct between your blinks. The psychological impact of this temporal distortion would be profound if you were still capable of coherent thought in the face of the tidal forces we discussed earlier. You would experience a form of cosmic loneliness beyond anything imaginable on Earth. The knowledge that with each subjective second that passes for you, everyone and everything you ever knew grows older by years, decades, or centuries. 25 miles from the event horizon, time dilation has reached a factor of thousands. Each second of your subjective experience corresponds to millennia in the outside universe. Stars visibly shift position in the sky as you watch, not from your motion but from their actual movement through space over centuries compressed into moments from your perspective. You witness stellar evolution in real time, stars being born from nebulae, maturing, expanding into red giants, and collapsing. Galaxies noticeably rotate, their spiral arms winding and unwinding like cosmic clock hands marking the passage of billions of years. 10 miles from the event horizon, the time dilation is now so extreme that the universe outside appears to be evolving at an accelerated rate visible to the naked eye. Galaxies collide and merge in what seems like minutes to you. The cosmic background radiation visibly shifts toward longer wavelengths as the universe's expansion accelerates. From your perspective, if any coherent you still exists at this point, the universe appears to be racing toward its heat death. The stelliferous era gives way to the degenerate era as stars wink out and fail to be replaced. White dwarfs cool to black dwarfs. Protons begin to decay, their half-lives of billions of years compressed into what seems like hours from your time-dilated frame. 5 miles from the event horizon, the time differential has become almost meaningless. Your wristwatch, if it could somehow remain intact against the tidal forces, would measure seconds while entire cosmic epochs unfold outside. You witness the universe aging trillions upon trillions of years in what feels like minutes. Here's the true cosmic horror of falling into a black hole from your perspective. You may witness the end of the universe before you reach the event horizon. Due to the extreme time dilation, trillions of years could pass outside while you experience just minutes of subjective time. Depending on the ultimate fate of the universe, whether it ends in a big freeze, big rip, big crunch, or some other cosmic finale, you might witness the universe's last moments during your fall. Imagine watching as the last stars burn out, as the last black holes evaporate through Hawking radiation, as the last particles of matter decay into radiation, as the universe reaches maximum entropy, a thin soup of photons and neutrinos stretched across an incomprehensibly vast and dark cosmos. All of existence winding down to its final state, and you still falling, still experiencing the last moments of your personal timeline while the universe concludes its own. This scenario assumes, of course, that you could somehow observe the outside universe despite the extreme blue shift of incoming light from your perspective, and the catastrophic tidal forces rearranging your atoms. It's a theoretical consideration rather than a practical one, but it illustrates the profound temporal displacement that occurs near a black hole. 1 mile from the event horizon, time dilation approaches infinity as you near the event horizon itself. From the perspective of a distant observer, if any could still exist in the ancient universe outside, you would appear to freeze at the horizon, never quite crossing it, your image growing dimmer and redder until it fades from detectability. But from your perspective, you cross the horizon without noticing anything special about that moment. There's no physical barrier, no membrane, no dramatic change in your local environment. The point of no return passes unmarked, except by the steadily increasing gravitational forces pulling at your component particles. This creates one of the deepest paradoxes in black hole physics, the apparent contradiction between what distant observers see or would see given sufficient time and visual acuity, and what the falling observer experiences. From the outside, nothing ever seems to cross the event horizon due to the infinite time dilation at the boundary. From the falling perspective, the horizon is crossed in a finite amount of proper time. This is not a contradiction but a consequence of the extreme warping of spacetime near a black hole. Different reference frames experience genuinely different realities, both equally valid from the perspective of general relativity. There's no privileged viewpoint that can claim to represent the true sequence of events. And here we encounter another mind-bending aspect of black hole physics, the breakdown of simultaneity. Near a black hole, the notion that events can be unambiguously ordered in time breaks down completely. Two events that appear simultaneous to you might appear separated by eons to a distant observer, or vice versa. This loss of temporal ordering adds another layer of existential horror to your fall. Not only are you spatially separated from the rest of the universe by the event horizon once you cross it, but you're also in a very real sense temporally dislocated. The universe you knew continues along a timeline increasingly divergent from your own, accelerating away from you temporally just as surely as it's separated from you spatially. Inside the event horizon, the temporal distortions become even more extreme. The direction toward the singularity, previously a spatial direction, becomes time-like, meaning that avoiding the center becomes as impossible as avoiding the future. Just as you inevitably move forward in time under normal circumstances, you inevitably move toward the singularity once inside the horizon. This transformation of space into time and time into space is perhaps the most profound aspect of black hole physics. It represents a fundamental reshaping of reality itself, where the familiar dimensions by which we navigate the universe are rearranged into an alien configuration that defies intuition. The time dilation effects near a black hole have implications not just for your subjective experience, but for fundamental physical processes as well. Chemical reactions slow down in your reference frame compared to the outside universe. Nuclear decay stretches out. Even quantum fluctuations, the random jitter of particles popping in and out of existence, occur at a reduced rate from your perspective. This temporal stretching affects everything, from the firing of neurons in what remains of your brain to the oscillation of atoms in what remains of your body. All processes slow down relative to the outside universe, creating a kind of temporal molasses that thickens as you approach the event horizon. But there's another temporal effect that adds to the nightmare, the increasing irreversibility of your journey. As you fall closer to the black hole, the amount of energy required to escape increases exponentially. This creates a thermodynamic arrow of time pointing inexorably inward, separate from but aligned with the relativistic effects we've been discussing. The temporal horror of falling into a black hole isn't just about time flowing at different rates, it's about the loss of temporal freedom, the reduction of possible futures to a single inevitable path leading to the singularity. Each meter of your fall reduces the space of possible futures available to you, narrowing your world line to an increasingly constrained trajectory. This loss of degrees of freedom represents a kind of entropy increase, a reduction in the information content of your possible futures, and it connects directly to one of the deepest problems in theoretical physics, the black hole information paradox, which we'll explore later. For now though, let's consider one more aspect of time dilation near black holes, its effect on quantum processes. According to quantum mechanics, particles and fields are constantly fluctuating, popping in and out of existence on timescales so short they're essentially undetectable under normal circumstances. Near the event horizon, these quantum fluctuations are stretched out by time dilation. Virtual particles that would normally exist for only attoseconds might persist for much longer in your reference frame. This stretching of quantum timescales plays a crucial role in Hawking radiation, the process by which black holes gradually lose mass over time. In the vacuum of space, virtual particle pairs constantly pop into existence, then annihilate each other almost immediately. Near the event horizon, however, one particle from a pair might fall into the black hole while the other escapes. From the perspective of a distant observer, the black hole appears to emit radiation, gradually losing mass in the process. This quantum evaporation occurs on timescales that are absurdly long for stellar mass black holes, roughly 10 to the power of 67 years, or 10,000 trillion 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 years. But from your time-dilated perspective near the event horizon, you might witness significant evaporation of the black hole during your fall, assuming you could somehow remain intact and conscious. Imagine watching as the black hole itself begins to shrink around you, its mass decreasing through quantum processes that should take longer than the current age of the universe many times over. From your perspective, the black hole's lifetime is compressed into observable periods, allowing you to witness cosmic processes normally spread across timescales far beyond human comprehension. In the final stages of evaporation, the black hole would release its remaining energy in a burst of high-energy radiation, a miniature Big Bang that would obliterate any matter in its vicinity. From your time-dilated perspective, you might witness this final explosion, seeing the death of the very object that has trapped you. Of course, all of this assumes you could somehow maintain cohesion and consciousness against the tidal forces and other effects we've discussed. In reality, your components would be reduced to elementary particles long before you could witness these ultra-long-term processes. But the theoretical possibility remains, highlighting the truly alien nature of time near a black hole. In that extreme environment, the familiar flow of seconds and minutes gives way to a temporal landscape as warped and distorted as the spatial dimensions around it. As the atoms that once constituted your body cross the event horizon, they enter a domain where time and space exchange roles, where the future becomes as physically constrained as a narrow corridor, where the singularity at the center exists not just somewhere but somewhen, an inevitable destination in both space and time. The time dilation nightmare of falling into a black hole represents one of the most profound challenges to our intuitive understanding of reality. It reveals time not as an absolute backdrop against which events unfold, but as a flexible dimension that warps and stretches in response to mass and energy. And for the particles that once constituted your conscious self, this temporal distortion is more than just a theoretical curiosity. It's the fundamental reshaping of their reality, a transformation of their world line from an open-ended path through space-time to a tightly constrained trajectory leading inexorably to the singularity. But before those particles reach the singularity, they encounter another horror of black hole physics, the accretion disk, a swirling maelstrom of superheated matter that surrounds many black holes like a luminous halo of destruction. This cosmic inferno adds another layer of extreme physics to your fall, introducing temperatures and radiation levels that make even the vacuum of space seem hospitable by comparison. Not all black holes are surrounded by accretion disks, those whirling maelstroms of superheated gas and dust. Some float in relative isolation, their immediate surroundings nearly as empty as the vacuum of deep space. If you were lucky enough to fall into one of these clean black holes, you'd experience only the gravitational and temporal effects we've discussed so far, the tidal spaghettification of your body and the extreme dilation of time. But the universe rarely offers such mercy. Most black holes, particularly the active ones that astronomers can actually detect, are messy eaters. As they pull in matter from their surroundings, perhaps a companion star, a gas cloud, or the debris of cosmic collisions, this material doesn't simply fall straight in. Due to conservation of angular momentum, it forms a flattened disk of orbiting matter around the black hole, the accretion disk. Imagine approaching such a black hole from a distance of several light years. The accretion disk appears as a bright ring around the black hole's silhouette. It glows across the electromagnetic spectrum, from radio waves to gamma rays, but particularly in X-rays and ultraviolet light. This is your first warning that you're not merely falling into gravitational extremes, but into a realm of extraordinary temperatures and radiation. As you draw closer, now within a light year of the system, the accretion disk resolves into a more complex structure. It's not a uniform ring, but a dynamic churning mass of gas and dust, with swirling vortices, shock waves and magnetic field lines made visible by the charged particles spiraling along them. From certain angles, you might also see jets of material being ejected from the poles of the black hole, narrow beams of particles accelerated to nearly the speed of light by the intense magnetic fields generated in the disk. At this distance, the radiation from the disk is already dangerous. Even with your ship's shielding, the X-ray and gamma-ray flux would deliver a lethal radiation dose within hours. The disk shines with the light of billions of stars concentrated in a region not much larger than a solar system, creating a radiation environment thousands of times more intense than the surface of a star. As your doomed approach continues, now within the orbital distance of Pluto from the black hole, the accretion disk dominates your view. It's no longer just bright, it's blindingly brilliant, a cosmic floodlight that outshines everything else in your field of view. The black hole at the center still appears as a dark circle, but it's now surrounded by concentric rings of light, each representing matter orbiting at different distances. These rings aren't stationary, they swirl and churn as material from the outer edges gradually spirals inward. Occasionally bright flares erupt as magnetic field lines reconnect or dense clumps of matter suddenly plunge toward the event horizon. The disk is a violent dynamic environment, a cosmic storm system powered by the black hole's gravity. At the distance of Earth's orbit from the Sun, roughly 93 million miles from the black hole, you encounter the outer edges of the accretion disk itself. Here the material is relatively cool, merely thousands of degrees, comparable to the surface of a star. But this is just the beginning of the temperature gradient. The accretion disk isn't just hot, it spans an extraordinary range of temperatures. The outer edges might be just a few thousand degrees, but as material spirals inward, losing angular momentum due to friction and magnetic effects, it heats up dramatically. By the time it reaches the inner regions near the event horizon, temperatures can exceed 10 million degrees hotter than the core of the Sun. As your ship penetrates the outer layers of the disk, you feel the first physical contact with this cosmic inferno. Particles of dust and gas strike your ship's hull, each impact releasing a tiny burst of energy. It's like flying through an increasingly intense hailstorm, except each hailstone carries not just kinetic energy, but thermal energy as well. The material in the disk isn't evenly distributed. It forms clumps and streams, areas of higher and lower density. Your ship might pass through relatively empty regions one moment, then plow into denser clouds the next. Each such encounter releases a shock wave of superheated plasma that washes over your vessel. At 10 million miles from the black hole well within the accretion disk, the environment becomes truly hellish. The temperature outside your ship now exceeds 100,000 degrees. Metal would not merely melt at this temperature, it would vaporize instantly. Only the most exotic materials could maintain structural integrity in such conditions, and even then only briefly. The radiation environment is equally extreme. X-rays and gamma rays stream from the inner regions of the disk, carrying enough energy to ionize atoms and break molecular bonds. If you could somehow survive the tidal forces and the heat, this radiation would still be instantly lethal, disrupting the chemical processes necessary for life at the most fundamental level. But it's not just electromagnetic radiation you need to worry about. The accretion disk is a violent, turbulent environment where particles are accelerated to significant fractions of the speed of light. Protons and heavier nuclei become natural cosmic rays, carrying kinetic energies millions of times greater than the most powerful particle accelerators on Earth can produce. These particles stream through your ship and your body, leaving trails of ionization that disrupt molecular structures. Each impact releases secondary particles, creating cascades of destruction at the atomic level. Even a single high-energy proton can shatter DNA molecules and other critical biological structures. At 1 million miles from the black hole, you encounter another phenomenon: magnetic reconnection. The accretion disk isn't just hot gas, it's a plasma, a state of matter where electrons have been stripped from atoms, creating a soup of charged particles. These particles generate their own magnetic fields as they move, and when magnetic field lines cross and reconnect, they release enormous amounts of energy in sudden explosive events. These magnetic flares can accelerate particles to even higher energies and generate intense bursts of radiation. From the outside they appear as sudden brightenings of the disk, lasting from seconds to hours. From within the disk there are apocalyptic events that release energy comparable to billions of nuclear weapons detonating simultaneously. As you continue your inward spiral, now at 100,000 miles from the event horizon, the accretion disk becomes even more extreme. Temperatures reach millions of degrees, hot enough to trigger nuclear fusion reactions in particularly dense regions. The disk becomes a chaotic nuclear furnace, synthesizing heavier elements from lighter ones in a process similar to what occurs in the cores of stars but far less controlled and far more violent. The radiation pressure, the physical force exerted by the intense flux of photons, becomes significant at this distance. Light itself pushes against your ship with measurable force, adding another vector to the complex interplay of gravity, magnetic fields and gas pressure that shapes the accretion flow. At 10,000 miles from the event horizon, you encounter the innermost stable circular orbit, ISCO, a critical boundary in the accretion disk. Beyond this point, stable orbital motion becomes impossible due to the extreme curvature of space-time. Material that crosses this boundary spirals rapidly inward, releasing enormous amounts of gravitational potential energy in a final burst of radiation before disappearing beyond the event horizon. This innermost region of the accretion disk is where the most extreme physics occurs. Temperatures exceed 10 million degrees. Magnetic field strengths approach those found in magnetars, the most magnetically intense objects known. Particles orbit at more than half the speed of light, their masses noticeably increased by relativistic effects. The radiation from this region is predominantly in the form of X-rays and gamma rays, with energies high enough to create particle-antiparticle pairs directly from pure energy. The environment is so extreme that quantum electrodynamics, the theory describing how light and matter interact, begins to show non-linear effects usually only observed in the most powerful laboratories on Earth. At 1,000 miles from the event horizon, you're now deep within the innermost region of the accretion disk. The black hole's silhouette dominates your forward view, a perfect circle of darkness surrounded by the brilliant maelstrom of superheated plasma. Gravitational lensing creates multiple images of the disk, with parts that are physically behind the black hole appearing above, below and around it from your perspective. The material around you is no longer recognizable as gas or plasma in any conventional sense. The temperatures and densities are so extreme that matter exists in exotic states not found naturally anywhere else in the universe. Electrons and nuclei form strange temporary bonds due to the intense magnetic fields. Quantum effects dominate the behavior of particles, creating phenomena that defy classical intuition. At 500 miles you begin to experience the direct interaction between the accretion disk and the black hole's event horizon. In a rotating black hole, which most real black holes are, the dragging of space-time interacts with the magnetic fields in the disk to extract rotational energy from the black hole itself. This process, called the Blandford-Zanagic mechanism, powers the relativistic jets that shoot out along the black hole's axis of rotation. These jets are among the most energetic phenomena in the universe, capable of projecting matter and energy across thousands or even millions of light-years. They consist of particles accelerated to more than 99% of the speed of light, collimated into narrow beams by intense magnetic fields anchored in the rotating disk. If your approach takes you near one of these jets, you encounter an environment even more extreme than the accretion disk itself. The particle density is lower, but the energies are higher, with individual particles carrying enough kinetic energy to be detectable from Earth as ultra-high energy cosmic rays if they happen to strike our atmosphere. At 100 miles from the event horizon, the combined effects of the accretion disk's heat, radiation and particle flux have long since reduced any physical structure, including your ship and your body, to a stream of ionized particles. These particles join the general flow of the accretion disk, becoming part of the final spiral into the black hole. Some of these particles might be captured by the magnetic fields and redirected into the polar jets, eventually being ejected from the system entirely. Others continue their inward spiral, radiating away energy as they fall deeper into the gravitational well. A small fraction, roughly 10% of the original mass that entered the outer edge of the disk, actually crosses the event horizon. The rest is converted to radiation through the processes we've described. This is one of the defining features of accretion disks. They're extraordinarily efficient at converting mass to energy. While nuclear fusion in stars converts less than 1% of rest mass to energy, accretion onto a black hole can convert more than 10 times that amount. This efficiency explains why accreting black holes are among the most luminous objects in the universe, outshining entire galaxies despite their relatively small size. As the particles that were once your body approach the event horizon, now just 10 miles away, they encounter one final extreme environment, the boundary layer where the accretion disk meets the event horizon itself. Here the orbital velocity of the disk material approaches the speed of light, creating extreme shear forces as faster-moving inner regions interact with slower-moving outer regions. These shear forces generate intense turbulence and magnetic instabilities, which in turn accelerate particles to even higher energies. The boundary layer glows with the highest energy radiation in the entire system, a last burst of electromagnetic fury before matter disappears forever beyond the event horizon. And finally those particles cross the invisible boundary, joining the black hole's mass. From the perspective of a distant observer, this crossing never quite completes. The extreme time dilation near the event horizon stretches the final approach to infinity. But from the reference frame of the particles themselves, the boundary is crossed in a finite and actually quite brief amount of proper time. Once beyond the event horizon, the fate of these particles is sealed. They join the inward spiral toward the singularity, their energy and information becoming part of the black hole's mass, angular momentum, and charge, the only three properties that according to classical general relativity, a black hole can possess. This then is the accretion disk inferno, a cosmic maelstrom of superheated plasma, intense radiation and powerful magnetic fields that adds another layer of extreme physics to the already mind-bending experience of falling into a black hole. It's an environment where temperatures exceed millions of degrees, where particles are accelerated to nearly the speed of light, where magnetic fields strong enough to tear apart atoms channel the flow of matter into complex structures. For any physical object, be it a spacecraft, a human body, or even a subatomic particle, the accretion disk represents a gauntlet of destruction that precedes the final plunge into the black hole itself. It ensures that matter doesn't simply fall into the black hole intact, but is first thoroughly transformed, broken down to its constituent particles and subjected to some of the most extreme conditions found anywhere in the universe. And yet, as hellish as the accretion disk is, it represents just one aspect of the black hole environment. Beyond the inferno of superheated plasma lies the even stranger realm of the photon sphere, where light itself orbits in perfect circles and visual reality becomes a hall of mirrors beyond human comprehension. Let's explore this next layer of the black hole experience, where the behavior of light creates visual paradoxes that challenge our most fundamental intuitions about space and perception. Let's momentarily set aside the physical torments of tidal forces and superheated plasma to focus on something equally mind-bending but more subtle. What you would see if you could somehow maintain visual perception during your fall into a black hole. We're entering the realm of the photon sphere, where light itself orbits in perfect circles and visual reality fractures into a kaleidoscope of paradoxical images. To understand this phenomenon, we need to remember that black holes don't just affect matter, they warp the very fabric of space-time. And since light travels along the contours of space-time, following what physicists call null geodesics, the extreme curvature near a black hole bends light paths into bizarre configurations that defy our everyday visual intuition. At a specific distance from a non-rotating black hole, exactly 1.5 times the Schwarzschild radius, which defines the event horizon, something remarkable happens. Light that passes at exactly this distance can orbit the black hole in perfect circles. This spherical shell around the black hole is called the photon sphere, and it represents a critical boundary where the behavior of light becomes truly exotic. Imagine yourself at a safe distance, observing the black hole from afar. The photon sphere wouldn't be directly visible, but its effects would create the most striking feature of the black hole's appearance, the shadow. This is not the event horizon itself, which is too small to see, but rather the apparent size of the black hole due to how it bends light. As you move closer, approaching within a few thousand miles of the black hole, the visual distortions become increasingly pronounced. Stars that should be blocked by the black hole appear as rings of light around it, perfect circles of brightness called Einstein rings. These form when light from distant stars passes near the black hole and is bent around it, reaching your eyes from directions that seem to originate from all around the black hole's silhouette. The closer a light ray passes to the black hole, the more it bends. At distances just outside the photon sphere, light can orbit the black hole multiple times before either escaping to infinity or falling toward the event horizon. This creates not just one Einstein ring but a theoretically infinite series of them, each corresponding to light that orbits a different number of times before reaching your eyes. In practice, each successive ring becomes exponentially fainter, as most light either escapes after one partial orbit or falls into the black hole. But with perfect vision you would see a series of concentric rings surrounding the black hole, each showing the same background stars but with increasing time delays. The innermost rings would show the universe as it looked millions or even billions of years ago, creating a visual time machine of sorts. As you fall closer, now within range of the photon sphere itself at approximately 67 miles from the event horizon for a stellar mass black hole, the visual experience becomes even more bizarre. You begin to see multiple images of the same parts of the universe, stretched and distorted in different ways depending on how many orbits the light has completed around the black hole. The universe appears to wrap around you in impossible ways. In front of you lies the black hole's dark silhouette, but somehow you can also see what's behind you reflected in the space around the black hole. It's as if reality has been folded in on itself, with normal spatial relationships completely broken. Even more disorienting, you can see the back of your own head. Light that leaves the back of your spacesuit can orbit around the black hole and return to your eyes from the front. With enough magnification, you could literally watch the back of your own skull as you fall toward the event horizon. This self-image isn't instantaneous though. The light takes time to complete its orbit, creating a delayed version of yourself. Depending on how close the light passes to the photon sphere, this delay could be seconds, hours, or even years. You would see not just yourself as you are now, but as you were at various points in the past, creating a nested series of temporal reflections. As you fall through the photon sphere itself, reality fractures completely. Your visual field becomes a chaotic mess of repeated distorted images. The universe appears to loop back on itself in impossible ways. Normal spatial intuitions like in front of or behind lose meaning entirely as light from all directions reaches your eyes through the twisted paths of curved space-time. This visual chaos is more than just disorienting. It represents a fundamental breakdown in how we normally perceive and navigate space. Our brains evolved to process images in a flat or mildly curved space-time, where light travels in nearly straight lines. Near a black hole, this assumption fails catastrophically, creating a visual environment that no biological system could have evolved to comprehend. Inside the photon sphere, but still outside the event horizon, you enter a region where light behaves in even stranger ways. Some light rays spiral gradually inward toward the event horizon, while others spiral gradually outward toward escape. The dividing line between these two fates becomes increasingly thin as you approach the horizon, creating fractal-like patterns of escape and capture in the paths that light can take. This region creates another visual effect. Certain directions in your field of view become exponentially brighter or darker than others. Directions that align with escape trajectories for light appear blindingly bright, as they collect light from large portions of the outside universe. Directions that align with capture trajectories appear extraordinarily dark, as light along these paths falls inevitably into the black hole. The result is a pattern of brightness and darkness that doesn't correspond to actual objects, but rather to the geometry of light paths in curved space-time. It's as if you're seeing the abstract mathematical structure of space itself rather than the matter and energy it contains. As you fall closer to the event horizon, now just 20 miles away, another visual effect becomes apparent: gravitational blue shift and red shift. Light coming from the direction of the black hole appears redder than it should, as it must climb out of the gravitational well to reach you. Light coming from the direction away from the black hole appears bluer, as it falls down the gravitational well toward you. This creates a color gradient across your field of view, with normal colors in the perpendicular directions but increasingly red tones toward the black hole and increasingly blue tones away from it. The magnitude of this shift grows as you approach the horizon, eventually reaching the point where visible light shifts entirely out of the visible spectrum in both directions, becoming infrared toward the black hole and ultraviolet away from it. At 10 miles from the event horizon, the visual distortions reach their peak. The entire universe appears to be concentrated in a bright ring behind you, with all the light from all directions except directly toward the black hole, squeezed into a narrow band. This is the exit cone, the solid angle through which light can still escape to the outside universe from your current position. As you fall closer to the event horizon, this exit cone shrinks, the bright ring contracting and dimming. At 5 miles out, it occupies perhaps 20 degrees of your field of view. At 1 mile, less than 5 degrees. The rest of your visual field is filled with the darkness of the black hole itself, not because light can't reach you from other directions, but because light from those directions is falling inward along with you, unable to escape to the outside universe. And finally, as you cross the event horizon, an invisible boundary with no local physical significance, the exit cone shrinks to nothing and winks out. There are no more directions in which light can escape. Everything you see now comes from inside the event horizon, light that is falling inward along with you. This doesn't mean you're suddenly plunged into darkness. Light still reaches your eyes from other parts of the interior of the black hole, but it's light that shares your fate, doomed to fall toward the singularity. You can still theoretically see other objects that fell in before you, illuminated perhaps by light that entered the horizon alongside them. But there's another visual effect that comes into play inside the event horizon: the reversal of space and time directions. Outside the horizon, the radial direction toward or away from the black hole is spatial. You can move either way, at least in principle. Inside the horizon, this direction becomes temporal. Moving toward the singularity becomes as inevitable as moving forward in time. This has profound implications for what you see. The singularity isn't just ahead of you, it's in your future, an inevitable destination in both space and time. Looking down toward the singularity is, in a very real sense, looking into the future. Looking up toward the event horizon is looking into the past. This temporal quality of space inside the horizon creates visual effects with no analog in normal experience. Light from events that are in your future closer to the singularity can reach you, allowing you to see the future in a very literal sense. Light from parts of the black hole interior that are in your causal future can travel backward relative to the outside time direction to reach your eyes. The visual experience inside the horizon thus becomes not just spatially distorted, but temporally inverted. Cause and effect seem to operate in reverse from some perspectives. You might see events before they occur relative to your proper time, a genuine form of visual precognition allowed by the extreme warping of space-time. All of these visual phenomena, Einstein rings, multiple images, self-images, exit cones, temporal inversions, combine to create what might be the most alien perceptual environment possible within the laws of physics. It's a realm where seeing is no longer believing, where visual intuition fails completely, and where the act of perception itself becomes a profound philosophical problem. But the photon sphere creates more than just visual distortions. It also represents a fundamental transition in the behavior of light, and by extension information near a black hole. At the photon sphere, information carried by light can become trapped in orbit, neither escaping to the outside universe, nor falling immediately into the black hole. This trapping of information plays a crucial role in the quantum mechanics of black holes. The photon sphere is where information begins to get smeared out and scrambled, a process that eventually leads to the infamous black hole information paradox. Light rays that orbit just above the photon sphere for extended periods carry information about the black hole's environment that becomes increasingly scrambled with each orbit. Physically, the photon sphere also marks a transition in the stability of orbits around the black hole. Outside the photon sphere, objects can maintain stable circular orbits indefinitely, just as planets orbit stars. Inside the photon sphere, no stable circular orbits exist. Any object must either fall into the black hole or escape to infinity. This means that the photon sphere represents a kind of tipping point in the black hole's gravitational influence. Beyond this boundary, the inexorable pull toward the event horizon becomes dominant, and escape requires increasingly precise initial conditions and increasingly large amounts of energy. For photons, particles of light with zero rest mass, the photon sphere represents a knife's edge between escape and capture. A photon passing exactly at the photon sphere with exactly tangential motion will orbit forever in theory. A photon passing slightly closer will spiral into the black hole. A photon passing slightly farther will spiral outward and escape. This extreme sensitivity to initial conditions creates a fractal structure in the fate of light rays near the photon sphere. Zoom in on the boundary between capture and escape, and you find an infinitely complex pattern of light paths that orbit the black hole different numbers of times before either escaping or falling in. This fractal pattern in light paths creates corresponding fractal patterns in what an observer near the photon sphere sees. The visual field becomes a kind of Mandelbrot set of light and dark regions, with infinitely detailed structure at all scales. It's as if the black hole is generating a visual representation of chaos theory through the behavior of light in its gravitational field. Another fascinating aspect of the photon sphere is its role in determining the black hole's shadow, the apparent size of the black hole as seen by distant observers. Because light that passes closer than the photon sphere inevitably falls into the black hole, the shadow appears larger than the event horizon itself. In fact, for a non-rotating black hole, the shadow has a radius exactly 27/2 times the event horizon radius, or approximately 2.6 times larger. This shadow is what astronomers actually observe when they create images of black holes like the famous one of M87* captured by the Event Horizon Telescope. The dark central region in such images isn't the event horizon directly, but rather the shadow created by the photon sphere's effect on light paths. For rotating black holes, the situation becomes even more complex. The photon sphere deforms, becoming oblate and asymmetric due to the black hole's spin. Light rays can now travel in either the same direction as the black hole's rotation, or against it, creating different orbital radii for prograde and retrograde photon orbits. This asymmetry creates corresponding asymmetry in the black hole's shadow and in the visual distortions experienced by a falling observer. The side of the black hole rotating toward you appears smaller and bluer due to relativistic beaming, while the side rotating away appears larger and redder. The combined effect creates a distinctive D-shaped shadow that's brighter on the side moving toward the observer. As you fall toward a rotating black hole, this asymmetry creates a swirling visual field, as if the universe is being flushed down a cosmic drain. Stars appear to orbit around the black hole's silhouette, their trails stretching into spiral patterns that trace the underlying rotational geometry of space-time itself. This rotation of space-time, technically called frame dragging or the lens-thirring effect, creates additional visual complexity. Light rays no longer move in simple curved paths but in three-dimensional twisted trajectories, like ribbons wrapping around the black hole at different angles. The visual chaos this creates is perhaps the purest expression of what makes black holes so fascinating and terrifying. They are regions where reality itself becomes plastic, where the fundamental structures we take for granted, like the straight-line propagation of light or the clear distinction between space and time directions, break down completely. And yet, all of these visual phenomena occur outside the event horizon. You can in principle still escape from the photon sphere or any point outside the horizon. Once you cross that critical boundary, however, the rules change completely. No amount of acceleration, no technological intervention, no physical process within the known laws of physics can prevent your journey to the singularity. This final boundary, the event horizon itself, represents perhaps the most profound transition in the black hole experience. It's not a physical surface, but a point of no return, a one-way membrane in the causal structure of space-time, and crossing it, despite its lack of local physical significance, changes everything about your relationship to the rest of the universe. We've discussed the approach to a black hole, the spaghettification of your body, the dilation of time, the inferno of the accretion disk, and the visual distortions of the photon sphere. But all of these horrors and wonders occur outside the event horizon, the infamous boundary that defines the black hole itself. Now we come to the most profound moment in our journey, crossing the point of no return. The event horizon is perhaps the most misunderstood aspect of black holes. It's often imagined as a physical surface, a dark membrane stretched across the void. But this is profoundly incorrect. The event horizon is not a thing but a condition. Specifically, it's the boundary in space-time beyond which the gravitational pull becomes so strong that even light cannot escape. What makes the event horizon so philosophically disturbing is that it's an invisible, intangible boundary with no local physical significance. If you were falling past it, you wouldn't feel anything special at the moment of crossing. No alarm would sound, no barrier would rupture. Your local environment would appear to change continuously, with no indication that you just crossed the most significant threshold in astrophysics. And yet, from that moment on, your fate is sealed. No force in the universe, no technology, no physical process within the laws of physics as we understand them can prevent your ultimate journey to the singularity. The event horizon represents a one-way door in the causal structure of space-time itself. This one-way nature of the event horizon leads to one of the deepest paradoxes in black hole physics, the apparent contradiction between what different observers experience. From your perspective as you fall in, the horizon crossing is a non-event, just another moment in your continuous trajectory. But from the perspective of an outside observer watching your fall, you never quite reach the horizon. Due to the extreme gravitational time dilation we discussed earlier, an external observer sees your fall slow asymptotically as you approach the horizon. Your image becomes increasingly redshifted and dimmer, but to them you remain frozen just above the horizon for all eternity, or at least until the black hole itself evaporates through Hawking radiation billions upon billions of years later. This isn't a perceptual illusion or a limitation of observation technology. It's a genuine feature of how space-time behaves in extreme gravitational fields. The same event, your crossing of the horizon, exists in your future, if you're observing from outside, but in your past if you've already fallen in. Different reference frames disagree not just about when things happen, but about whether they've happened at all. This relativity of simultaneity reaches its most extreme form at the event horizon. Events that appear simultaneous to you might be separated by eons from an outside perspective. Conversely, events that outside observers consider to happen at vastly different times might appear nearly simultaneous to you as you fall in. But let's focus on your direct experience. Imagine that through some miraculous technology you've survived the tidal forces, the radiation, and all the other hazards we've discussed. You're now just moments away from crossing the event horizon, perhaps 10 miles out from a stellar mass black hole. At this distance, your view of the outside universe has condensed into a small bright circle behind you, the exit cone through which light can still escape to infinity. Ahead of you lies the apparent darkness of the black hole, though what you're seeing isn't the horizon itself but rather the absence of light coming from that direction. Your instruments show nothing unusual about the space ahead. Radiation detectors, gravitational field sensors, accelerometers, all register strong but smoothly varying values. There's no discontinuity, no spike, nothing to indicate you're approaching a fundamental boundary in space-time. 5 miles from the horizon, the exit cone has shrunk further, now occupying just a few degrees of your field of view. The time dilation relative to distant observers has become extreme. Each second you experience corresponds to years or decades for observers far from the black hole. Your communication signals to the outside world are now severely redshifted, stretched to much longer wavelengths by the gravitational field. A radio message sent at gigahertz frequencies would be received as megahertz or kilohertz. A visible light signal would shift to infrared or radio waves. Eventually your signals become so stretched that they contain too little energy to be detected at all. 1 mile from the horizon, the exit cone is now just a bright point behind you, a single star-like aperture through which you can glimpse the universe you're leaving behind. Time dilation has reached factors of thousands or millions. Each heartbeat, each thought, each Planck time of your experience corresponds to vast epochs in the outside universe. And then without fanfare, without physical sensation, you cross the event horizon itself. The exit cone winks out completely. There are no more directions in which light can escape. But contrary to popular imagination, you don't suddenly find yourself in darkness. Light still reaches your eyes from sources inside the horizon, including light that fell in along with you or before you. The most profound change is not what you can see but the restructuring of space-time around you. Outside the horizon, the radial direction toward or away from the black hole is spatial. You can move either way, at least in principle. Inside the horizon, this radial direction becomes temporal. Moving toward the singularity becomes as inevitable as moving forward in time. This transformation of space into time and time into space represents the deepest horror of falling into a black hole. It's not just that escape is impossible, it's that the very concept of escaping loses meaning. Asking how to get out of a black hole becomes as meaningless as asking how to travel to yesterday. The direction outward no longer exists as a spatial path you could follow. Another way to understand this outside the horizon, the future light cone, the set of all possible paths that light or anything else can take from your current position, extends outward in all directions, including away from the black hole. Inside the horizon, this future light cone tips over so dramatically that all possible future paths lead toward the singularity. There literally is no direction, no velocity, no physical process that leads away from the central singularity. This tipping of the light cones inside the horizon creates another disturbing effect, causal disconnection from the rest of the universe. Once you cross the horizon, you can never again affect or communicate with anything outside. From the perspective of the external universe, you effectively cease to exist as a causal agent. You can no longer send signals, influence events, or leave any trace of your existence on the outside world. Conversely, much of the outside universe becomes causally disconnected from you. Events that occur in distant regions after you cross the horizon from your perspective can never affect you. Information about those events cannot reach you before you encounter the singularity. Your slice of reality shrinks inexorably as you fall deeper, with more and more of space-time becoming permanently unobservable and unreachable. This causal disconnection represents an existential horror beyond physical destruction. It's a form of isolation more profound than any experienced in the external universe. No prison, no exile, no solitary confinement can compare to the absolute causal quarantine imposed by the event horizon. And yet, from a local perspective, the space around you still appears three-dimensional. You can still move sideways in directions perpendicular to the radial. You can still orbit around the black hole's center, albeit briefly. These degrees of freedom remain temporarily available to you, even as the inevitability of your journey to the singularity becomes absolute. For a non-rotating Schwarzschild black hole, your remaining proper time, the time you experience locally, before reaching the singularity is roughly proportional to the black hole's mass. For a solar mass black hole, you have approximately microseconds. For a supermassive black hole like the one at the center of our galaxy, you might have hours or days. This remaining lifetime has an interesting property. It's independent of where you cross the horizon, whether you fall directly inward, or spiral in gradually, Once you're inside, your fate is sealed with the same cosmic timer. This remaining proper time is a fundamental property of the black hole's interior geometry, as inescapable as the flow of normal time in the outside universe. For a rotating Kerr black hole, the situation becomes more complex. The event horizon deforms due to the black hole's spin becoming oblate rather than spherical. More significantly, the space inside the horizon has different properties, potentially allowing for slightly longer survival times and more complex trajectories before the inevitable encounter with the singularity. In a Kerr black hole, the singularity takes the form of a ring rather than a point, and it's technically possible to pass through the center of this ring without hitting the singularity itself. This doesn't allow escape, you're still trapped inside the event horizon, but it does create a more complex interior geography with additional regions and boundaries. Some Kerr black holes even have inner horizons, second boundaries inside the event horizon, where the light cones straighten out briefly before tipping over again. These inner horizons have unusual properties, but they don't provide an escape route. At best, they briefly delay the inevitable journey to the singularity. Regardless of the black hole's rotation, crossing the event horizon represents an irreversible transition in your relationship to the rest of the universe. You've entered a domain where normal physical intuitions fail, where escape becomes not just practically impossible but conceptually meaningless, and where your future contains only one possible destination, the singularity. But this classical picture, based purely on Einstein's general relativity, isn't the whole story. Quantum mechanics adds another layer of complexity to the horizon crossing, introducing phenomena that challenge our understanding of information, causality, and the nature of space-time itself. When quantum effects are taken into account, the event horizon becomes more than just a one-way boundary. It becomes a region where information appears to be both destroyed and preserved, where particles can be both inside and outside simultaneously due to quantum entanglement, and where the fundamental principles of physics come into apparent conflict. This quantum perspective introduces new questions. What happens to the information contained in matter that falls into a black hole? Is the horizon crossing truly irreversible? Or does quantum mechanics offer some escape clause? Do black holes preserve or destroy information? These questions lead us to the infamous black hole information paradox, where quantum mechanics and general relativity give seemingly contradictory answers. From a quantum mechanical perspective, the horizon crossing becomes less defined. Quantum uncertainty blurs the precise location of the horizon, creating a fuzzy boundary rather than a sharp division. Particles can tunnel across this boundary through quantum processes, leading to phenomena like Hawking radiation, the slow leakage of energy from black holes that eventually causes them to evaporate. This quantum fuzziness doesn't provide an escape route for a macroscopic object like you. The probability of quantum tunneling scales with mass, becoming exponentially negligible for anything larger than elementary particles. But it does mean that the classical picture of the horizon as an absolute boundary requires modification. Another quantum effect, horizon crossing, entangles you with the black hole in a fundamental way. The quantum state of particles that fall in becomes correlated with the state of the Hawking radiation emitted by the black hole. This entanglement is crucial for preserving information, at least theoretically, but it doesn't help you personally escape your fate. These quantum considerations transform our understanding of what it means to cross the event horizon. It's no longer just a journey past a point of no return, it's an integration into the black hole's quantum state, a dissolution of your information into the complex quantum system that is the black hole itself. For you personally, however, these quantum subtleties make little practical difference. Once you cross the horizon, your future still contains only the singularity. Quantum mechanics might preserve your information in some abstract sense, encoded in correlations between Hawking radiation particles, but it doesn't preserve you as a conscious entity or offer a path back to the outside universe. The horizon crossing thus represents the ultimate one-way journey, a transition from the domain where normal physical laws and intuitions apply to a realm where space becomes time, where all paths lead to a single destination, and where your connection to the rest of the universe is irrevocably severed. It's worth emphasizing again, there's nothing physically special about the horizon itself. If you could somehow survive the tidal forces and other hazards, you wouldn't feel anything unusual as you crossed it. No local experiment you could perform would tell you definitively that you've passed the point of no return. Only global considerations. The causal structure of space-time, the ultimate destinations of light rays, the complete map of possible futures, reveal the significance of this boundary. This nothing special locally property of the event horizon is perhaps its most insidious aspect. You could cross it without realizing what's happened, without alarms or warnings, only to discover later that escape has become impossible. It's a trap without bars, a cage without walls, a prison defined purely by the geometry of space-time itself. And once inside this invisible cage, your remaining existence has only one possible conclusion: an encounter with the singularity, where tidal forces become infinite, where space-time curvature reaches values beyond mathematical description, and where our current understanding of physics breaks down completely. This inevitable journey to the singularity is the final chapter in the black hole experience, a confrontation with the edge of physics itself, where general relativity predicts its own failure, and where the quantum nature of space-time finally becomes unavoidable. But before we descend into that ultimate abyss, let's examine more closely the quantum aspects of black holes and the infamous information paradox that has challenged physicists for decades. So far we've primarily discussed black holes through the lens of Einstein's general relativity, the theory that describes gravity as the curvature of space-time. But general relativity is an incomplete description of nature. It doesn't account for quantum mechanics, the framework that governs the behavior of matter and energy at the smallest scales. When we try to apply quantum principles to black holes, we encounter some of the deepest paradoxes in theoretical physics, puzzles that challenge our understanding of reality at its most fundamental level. These quantum conundrums don't just add complexity to the black hole story, they potentially rewrite it completely. Let's begin with a simple question that leads to profound consequences. What happens to information that falls into a black hole? By information, physicists don't just mean data or knowledge in the conventional sense. They're referring to the precise quantum state of a system, the complete specification of all particles, their positions, momenta, spins, and other properties. According to quantum mechanics, this information should never be truly lost. It might be scrambled or transformed, but the fundamental laws of physics suggest it must be preserved in some form. Classical general relativity, however, tells a different story. According to Einstein's theory, anything that falls into a black hole contributes only to its mass, angular momentum, and electric charge. All other details, what the object was made of, its shape, its composition, its quantum state, are irretrievably lost. This principle is often summarized in John Wheeler's phrase, "Black holes have no hair," meaning they lack distinguishing features beyond those three basic properties. This tension between quantum mechanics' insistence that information must be preserved and general relativity's claim that black holes destroy information is the essence of the black hole information paradox. It's not just an academic disagreement, it's a fundamental inconsistency between our two most successful physical theories. So what happens to you, or more precisely, to the quantum information that constitutes you, when you fall into a black hole? Does this information disappear forever, violating the principles of quantum mechanics, or is it somehow preserved, contradicting the predictions of general relativity? The plot thickens when we consider Hawking radiation, the slow thermal emission from black holes predicted by Stephen Hawking in the 1970s. According to Hawking's original calculation, this radiation is perfectly thermal, carrying no information about what fell into the black hole. If a black hole eventually evaporates completely through this process, all information about its contents would seem to be permanently lost, a clear violation of quantum principles. This paradox has driven theoretical physics research for decades, leading to increasingly exotic proposals for its resolution. Let's explore some of these potential solutions and their implications for your fate as you fall into the abyss. One prominent approach focuses on the event horizon itself. Perhaps the traditional picture of a sharp, well-defined boundary is incorrect when quantum effects are considered. Instead, the horizon might be a fuzzy region where quantum fluctuations create uncertainty about its precise location and properties. In this quantum-corrected picture, the horizon becomes a complex, dynamic system rather than a simple geometric boundary. It might store information in subtle quantum correlations, tiny entanglements between the internal quantum state of the black hole and the Hawking radiation it emits. This perspective has led to concepts like the firewall hypothesis, which suggests that the event horizon isn't the smooth transition predicted by general relativity, but rather a region of intense high-energy physics. Passing through this firewall would destroy any coherent quantum state, essentially burning up the information carried by infalling matter and transferring it to the radiation. If this hypothesis is correct, your crossing of the event horizon wouldn't be the uneventful passage predicted by classical physics. Instead, you'd encounter a wall of high-energy particles and extreme quantum fluctuations that would instantly destroy your physical form, transferring your quantum information to the radiation field around the black hole. Another approach, championed by theoretical physicist Leonard Susskind and others, is called black hole complementarity. This proposal suggests that the apparent contradiction arises because we're trying to simultaneously apply descriptions that are only valid from different perspectives. From your perspective, as you fall into the black hole, you pass through the horizon normally and encounter the singularity, with your information seemingly lost. From the perspective of an outside observer, you never quite reach the horizon due to time dilation, and your information remains encoded in a hot membrane at the horizon, eventually to be released via Hawking radiation. Complementarity suggests that these two descriptions, though seemingly contradictory, are actually complementary, both valid in their respective domains but impossible to apply simultaneously, much like the wave and particle descriptions of light in traditional quantum mechanics. If complementarity is correct, the information paradox is resolved through a kind of cosmic bookkeeping trick. Information isn't lost, it's just described differently, depending on the reference frame. However, this resolution comes at the cost of challenging our intuitive notion that there should be a single observer-independent reality. A third approach involves holography, the idea that all the information about a region of space can be encoded on its boundary. The most developed version of this concept is the AD-SAL-CFT correspondence, proposed by Juan Maldacena in 1997, which suggests that a gravitational system like a black hole is mathematically equivalent to a quantum field theory living on its boundary. In this framework, when you fall into a black hole, your information isn't truly inside the black hole in the conventional sense. Instead, it's encoded in the quantum state of the boundary theory, from which it can eventually be recovered. The interior of the black hole becomes a kind of holographic projection, a geometric representation of information that fundamentally resides elsewhere. If holography is the correct resolution, then your fall into a black hole represents not a journey into a physical interior, but rather a translation of your information into a different representational format. You still experience the fall subjectively, but what's really happening is a complex rearrangement of quantum information at the boundary. Perhaps the most radical proposal comes from theories suggesting that black holes create new universes. When matter collapses to form a black hole, it might bounce rather than forming a singularity, creating a new expanding region of space-time, essentially a baby universe, connected to our universe only through the black hole. In this scenario, your information isn't lost, because it continues to exist in the new universe. From your perspective, falling into the black hole would be like passing through a one-way door into an entirely new cosmos with its own laws and evolution. This possibility connects to speculative ideas like the fecund universes theory, which suggests that black holes are cosmic reproductive organs, with each one giving birth to a new universe with slightly different physical parameters. If this were true, your fall into a black hole would be not an end but a transition, a cosmic reincarnation into a newly born reality. All these proposals share a common theme. They suggest that the traditional picture of information being irretrievably lost in a black hole is incorrect. One way or another, information must be preserved, even if the mechanisms for this preservation challenge our intuitive understanding of space, time, and reality. But what does this mean for you personally as you fall into a black hole? Does the preservation of your quantum information in some abstract sense offer any comfort or hope? Unfortunately, no. Even if your information is preserved in Hawking radiation, encoded on the horizon, or transferred to a baby universe, you as a conscious entity would still experience destruction. The preservation of information doesn't imply the preservation of consciousness or identity in any meaningful sense. Think of it this way. If a book is burned and its exact atomic configuration is recorded before destruction, the information content of the book isn't lost. But the book as a functional object, something that can be read and understood, is still gone. Similarly, the preservation of your quantum information doesn't mean you continue to exist as a thinking, feeling being. This distinction between information preservation and practical survival highlights a philosophical aspect of the information paradox, the gap between physical descriptions and subjective experience. Physics can tell us what happens to your constituent particles and their quantum states, but it remains silent on what happens to you as a conscious observer. This brings us to another quantum aspect of black holes, the role of the observer. Quantum mechanics assigns a special role to observation, suggesting that the state of a system depends on how it's measured. Near a black hole, this observer dependence becomes especially profound. Different observers can disagree radically about the basic nature of events near the event horizon. An infalling observer sees nothing special at the horizon and perceives a continued journey toward the singularity. A distant observer sees infalling matter slow down asymptotically, never quite reaching the horizon due to time dilation. These different perspectives aren't just differences of opinion, they represent fundamentally different physical descriptions, each valid in its own domain. This relativity of description challenges the notion that there must be a single, observer-independent reality, a challenge that becomes acute in the quantum realm. The black hole interior represents a domain where quantum effects and gravitational effects become equally important, a regime where neither quantum mechanics nor general relativity alone provides a complete description. This is the realm of quantum gravity, a still incomplete theory that would unify these fundamental frameworks. Various approaches to quantum gravity, string theory, loop quantum gravity, causal set theory, and others offer different predictions about what happens at the quantum level as you fall into a black hole. Some suggest that space-time itself dissolves into more fundamental constituents like strings or loops. Others propose that space-time is fundamentally discrete rather than continuous, composed of individual atoms of space and time. In these quantum gravity scenarios, your fall into a black hole might end not at a singularity of infinite density, but at a region where space-time itself ceases to be a meaningful concept. You wouldn't just be torn apart physically, the very notion of space and time in which this tearing occurs would break down, replaced by something more fundamental but currently beyond our mathematical description. Another quantum complication, the uncertainty principle. In quantum mechanics, position and momentum cannot both be precisely determined simultaneously. This fundamental uncertainty, applied to the gravitational field itself, suggests that the exact location of the event horizon cannot be precisely known. It fluctuates quantum mechanically. These horizon fluctuations create a region of uncertainty around the classical horizon radius, sometimes called the quantum atmosphere of the black hole. This region isn't just conceptually fuzzy, it's physically active, with virtual particles constantly popping in and out of existence, occasionally resulting in the emission of real particles as Hawking radiation. If you fall through this quantum atmosphere, you'd encounter not a smooth, well-defined boundary, but a seething quantum foam of space-time fluctuations. These fluctuations would interact with your own quantum state in unpredictable ways, potentially affecting the specific manner in which your information is processed by the black hole. Even the basic concept of falling in becomes ambiguous in this quantum picture. Due to quantum uncertainty, there's a non-zero, though typically minuscule, probability that you could quantum tunnel out of the black hole, essentially teleporting across the horizon through a quantum process. For macroscopic objects like humans, this probability is so vanishingly small as to be effectively zero, but it illustrates how quantum mechanics blurs the seemingly absolute boundary defined by the event horizon. Quantum considerations also raise the possibility of remnants, stable or long-lived objects that remain after a black hole evaporates. These remnants might store the information that fell into the black hole, resolving the information paradox by preserving this data until the black hole's demise. If remnants exist, your information might ultimately reside in one of these exotic objects after the black hole that consumed you evaporates billions of years later. Again, this wouldn't constitute survival in any meaningful sense, but it would mean that the universe retains some record of your existence even after the black hole itself is gone. Perhaps the most mind-bending quantum aspect of black holes is the holographic principle, which suggests that the entire interior of a black hole can be completely described by information encoded on its two-dimensional surface. This principle extends beyond black holes to suggest that our entire three-dimensional universe might be encodable on a distant two-dimensional surface, a cosmic hologram of sorts. In this holographic framework, your fall into a black hole represents not a journey into a physical interior, but a translation of your information into a different coding on the horizon itself. The three-dimensional experience of falling would be a kind of illusion, a holographic projection from information stored on the horizon. All these quantum considerations, information preservation, observer dependence, uncertainty, holography, represent not just technical complications but fundamental challenges to our understanding of reality. They suggest that near a black hole, the basic concepts we use to make sense of the world, space, time, causality, identity, break down or transform in profound ways. For you as a falling observer, these quantum complications don't offer escape or salvation. They don't nullify the crushing tidal forces or provide a route back to the outside universe. But they do suggest that your destruction is more complex, more ambiguous, and perhaps more meaningful in the cosmic scheme than the simple picture of being crushed at a singularity. Your information, in some abstract sense, persists. It becomes entangled with the black hole's quantum state, potentially encoded in subtle correlations that will eventually manifest in the pattern of Hawking radiation emitted over billions of years. Parts of your quantum essence might tunnel back out, might reside in a remnant, might seed a new universe, or might be holographically encoded on the horizon. None of these possibilities constitute survival as we normally understand it. You still experience destruction, your consciousness still ends, but from the perspective of fundamental physics, your fall into a black hole isn't a simple erasure from reality. It's a complex transformation, a redistribution of your quantum information into forms and channels we don't yet fully understand. This quantum perspective transforms the black hole from a cosmic garbage disposal that simply destroys information to a kind of cosmic computer that processes information in profoundly alien ways. Your fall becomes not an end but a translation from the language of ordinary matter and energy to the exotic tongue of black hole physics. And at the core of this translation process lies the most mysterious entity in theoretical physics, the singularity, the point where space-time curvature becomes infinite, and our current theories officially break down. But quantum considerations suggest that this classical singularity might not be the final word. Let's explore what might really await at the center of a black hole when quantum effects are taken into account. In classical general relativity, all world lines that cross the event horizon inevitably lead to a single destination, the singularity. This is not just a point of extreme density, it's a breakdown in the fabric of space-time itself, a location where the mathematics of Einstein's equations predict infinite curvature, infinite tidal forces, and infinite density. At the singularity, the laws of physics as we understand them simply cease to function. It's not merely that they become difficult to calculate, or that approximations fail. The equations themselves produce infinities, meaningless results that signal the theory has reached its limits. This breakdown is not a flaw in our mathematics, but an inherent feature of general relativity. Einstein's theory predicts its own failure at the singularity, a remarkable case of a theory explicitly identifying the boundaries of its applicability. It's as if the laws of physics contain a built-in warning sign. Beyond this point, these rules no longer apply. But what does it mean for the laws of physics to break down? And what actually happens at the singularity when quantum effects are taken into account? To understand this, we need to examine what physical quantities become infinite as you approach the singularity. The most important is the space-time curvature, which determines the strength of tidal forces. As you fall toward the singularity, the curvature increases without bound, reaching values where the distance between any 2 points seems to simultaneously be zero and infinite, a geometric impossibility in conventional mathematics. This infinite curvature creates tidal forces that approach infinity as well. Remember the spaghettification we discussed earlier. Near the singularity, this stretching effect becomes unlimited. The difference in gravitational pull between any 2 points, no matter how close together, becomes infinite. This means that any extended object, whether a human body, an atom, or even a fundamental particle with non-zero size, would be torn apart. Another quantity that approaches infinity is density. All the mass of the black hole appears to be concentrated at a single point of zero volume, creating infinite mass density. This infinite concentration challenges our understanding of matter itself. No known state of matter can exist at such densities, not even the exotic quark matter found in neutron stars or the quark gluon plasma of the early universe. These infinities signal that general relativity alone cannot describe the singularity. We need a theory that incorporates quantum mechanics, a theory of quantum gravity. While we don't yet have a complete, universally accepted theory of quantum gravity, various approaches provide hints about what might replace the classical singularity. One possibility comes from loop quantum gravity, which suggests that space itself has a discrete atomic structure at the smallest scales. In this framework, there's a minimum possible length, a quantum of distance below which the concept of shorter ceases to have meaning. This discreteness would prevent the formation of a true mathematical singularity of zero size, replacing it with an extremely dense but finite core. String theory offers another perspective. In string theory, the fundamental constituents of reality are not point particles but tiny vibrating strings. These strings cannot be compressed beyond a certain length, which again prevents the formation of a zero-size singularity. Instead, as matter collapses beyond a certain density, new physical effects emerge that prevent further collapse. One such effect is the theoretical conversion of a black hole into a fuzzball, a tangled ball of strings with a size approximately equal to the event horizon. In this picture, there is no singularity at all. The entire interior of the black hole is filled with a peculiar state of string theoretical matter that mimics the properties of a black hole when viewed from outside. Another possibility, motivated by various approaches to quantum gravity, is that the singularity is replaced by a bounce. As matter collapses to extreme densities, quantum gravitational effects create an outward pressure that counteracts gravity, causing the collapse to reverse. This could lead to an expanding region on the other side of the black hole, effectively a new universe being born. This scenario connects to the ideas of cosmic inflation and the multiverse. Each black hole might birth a new universe with slightly different physical parameters, leading to a vast cosmic tree of universes, each sprouting from black holes formed in parent universes. If true, your journey into a black hole would end not at a singularity, but with a transition into a newly forming cosmos. Yet another possibility comes from holographic approaches to quantum gravity. In these frameworks, the apparent three-dimensional interior of a black hole is actually encoded in information stored on its two-dimensional horizon. The singularity itself would be a kind of illusion, not a physical location, but an artifact of trying to describe the black hole's information content in inappropriate geometric terms. All these speculative frameworks share a common theme. They suggest that the true nature of the black hole's center involves physics beyond our current theories, exotic states of matter and energy, reconfigurations of space-time itself, or even transitions to other cosmic domains. But regardless of which, if any of these speculative theories turns out to be correct, your personal experience of approaching the singularity would be brief and violent. Even if the classical singularity is ultimately replaced by some exotic quantum gravitational object, the tidal forces near this central region would still be extreme enough to destroy any macroscopic object. Let's consider the specific stages of this final approach, assuming you've somehow remained intact until now, a physical impossibility, but useful for illustration. At 1 microsecond, before reaching the classical singularity location, tidal forces would exceed the strong nuclear force, the force that holds atomic nuclei together. Any remaining atomic nuclei would be forcibly torn apart into their constituent protons and neutrons. These nucleons themselves would be stretched and distorted beyond recognition. At 1 nanosecond out, even the internal structure of protons and neutrons would begin to distort. Quarks, normally confined within nucleons by the strong force, would experience tidal forces strong enough to overcome their binding. The distinction between different types of fundamental particles would begin to blur as the underlying quantum fields are stretched and contorted by the extreme space-time curvature. 1 picosecond from the classical singularity, the tidal forces would approach the Planck scale, the fundamental unit of force in quantum gravity, roughly 10 to the power of 44 newtons. At this scale, the smooth fabric of space-time itself begins to break down. Quantum fluctuations in the gravitational field become so extreme that the concept of a definite space-time geometry loses meaning. This is the domain of quantum foam, a state where space-time itself fluctuates wildly, with microscopic black holes and wormholes constantly forming and disappearing. Distance and duration become fuzzy probabilistic concepts rather than definite quantities. The arrow of time, which remained meaningful even inside the event horizon, now dissolves into quantum uncertainty. If you could somehow maintain perception in this region, you couldn't. You would experience not just the dissolution of your physical form, but the dissolution of the very concepts needed to make sense of experience. The notions of here, now, before, and after lose their meaning. Causality itself becomes a casualty of quantum gravitational effects. In this final approach to the quantum-corrected singularity, whatever its true nature, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, might unify into a single force. The distinct particles and fields that constitute ordinary matter would merge into a more fundamental substrate, perhaps strings or loops or something else entirely beyond our current theories. This unification of forces and dissolution of ordinary matter represents a return to conditions similar to those that existed in the first moments after the Big Bang, where the distinct forces and particles of our current universe had not yet differentiated from one another. In a sense, the center of a black hole connects to the beginning of cosmic time, creating a full circle in the life cycle of the universe. Indeed, some speculative theories suggest direct connections between black holes and the Big Bang itself. Perhaps our entire universe emerged from the other side of a black hole in some parent universe. Perhaps what we call the Big Bang was actually a big bounce from a previous cosmic cycle. These possibilities remain highly speculative, but illustrate how black hole singularities tie into our deepest questions about cosmic origins and ultimate fate. Regardless of which, if any of these speculative frameworks turns out to be correct, they all agree on one point. The classical picture of a singularity as a point of infinite density and curvature is almost certainly wrong. Quantum effects must modify this picture, replacing the mathematical singularity with something exotic but finite. This replacement of infinities with finite but extreme physics has precedent in other areas where classical theories break down. Before quantum mechanics, the electromagnetic theory of the atom predicted that electrons would spiral into the nucleus in a fraction of a second, emitting infinite energy as they did so. Quantum mechanics replaced this catastrophic prediction with the stable, quantized orbits we now know atoms possess. Similarly, quantum gravity is expected to tame the infinities predicted by classical general relativity, replacing them with extreme but ultimately finite physics. The exact nature of this replacement remains one of the greatest unsolved problems in theoretical physics. For you personally, however, these theoretical distinctions make little practical difference. Long before reaching the domain where quantum gravitational effects become dominant, tidal forces would have reduced you to elementary particles. Your atoms would have been torn apart by tidal forces exceeding the electromagnetic binding force. Your nuclei would have been shredded by tidal forces exceeding the strong nuclear force. The progression from macroscopic human to microscopic elementary particles represents not just a physical reduction but an informational one. The complex arrangements and relationships that constituted you as a person, the neural patterns of your brain, the genetic information in your DNA, the specific molecular configurations of your cells, all this structured information is lost as you're reduced to a stream of elementary particles. Or is it? This question brings us back to the information paradox we discussed earlier. Is this information truly destroyed, or is it preserved in some form? The answer depends on the true nature of the singularity and the correct theory of quantum gravity. If information is indeed preserved, as most physicists now believe, then your reduction to elementary particles doesn't represent a complete erasure. Your information is scrambled, transformed, encoded in new forms, perhaps in subtle quantum correlations, perhaps in the precise pattern of Hawking radiation that will eventually be emitted, perhaps in the state of some exotic quantum gravitational object at the black hole's center. This information preservation, however, offers no practical consolation. The specific arrangements of matter and energy that constituted your conscious self are irreversibly disrupted. The pattern that was you is scattered and transformed beyond recognition or recovery. There's a profound philosophical question here about identity and continuity. If all your constituent particles and all the information about their arrangement are preserved in some abstract sense, has you survived? Most would say no. The specific implementation of that information as a functioning conscious entity has been destroyed, even if the information itself persists in some transformed state. This distinction between information preservation and practical survival highlights a gap between the concerns of theoretical physics and those of human experience. Physics cares about the ultimate fate of information. Humans care about the continuity of consciousness and experience. As you approach the singularity, or whatever replaces it in a complete theory of quantum gravity, you cross a threshold beyond which physics itself becomes uncertain. Our best theories disagree or simply fail to provide answers. This region represents not just a physical boundary but an epistemological one, a limit to what can be known using our current frameworks. This limit to knowledge isn't merely a temporary gap in our understanding, it may represent a more fundamental boundary. Some physicists, including Stephen Hawking, have suggested that there might be aspects of the black hole interior that are in principle unknowable from the outside, that the complete physics of what happens beyond the event horizon cannot be fully captured by any external theory or observation. This proposition connects to broader questions about the limits of scientific knowledge. Are there aspects of reality that are permanently hidden from us? Regions where the very concept of scientific understanding breaks down? Or will a complete theory of quantum gravity eventually remove these apparent limits, providing a full account of what happens at the center of a black hole? We don't yet know the answer. The singularity stands at the edge of physics not just as a challenge to our current theories but as a test of the very project of scientific explanation itself. It asks whether our drive to understand the universe through mathematical models can extend to all domains or whether there are fundamental limits to this approach. For now, the singularity remains a horizon of knowledge, a boundary where our best theories fail, and where the true nature of reality remains obscured. It's a reminder of how much we still don't understand about the cosmos, despite our remarkable progress in exploring its patterns and processes. But while the true nature of the singularity remains unclear, there are speculative possibilities that offer a potential escape from the black hole fate, not for you personally, once you've crossed the event horizon, but for some trace of the information that constituted you. These speculative escapes involve exotic physics like wormholes, baby universes, and quantum tunneling. Let's explore these theoretical possibilities, keeping in mind that they remain highly speculative and may ultimately be ruled out by a complete theory of quantum gravity. We've established that once you cross the event horizon of a black hole, conventional physics offers no escape. The direction out becomes time-like rather than space-like, making escape as impossible as traveling backward in time. But theoretical physics is full of speculative ideas that might, emphasis on might, offer conceptual escapes from this seemingly absolute trap. These speculative possibilities don't offer practical salvation for someone who's fallen into a black hole. They won't save you personally, but they do suggest that the finality of a black hole might not be as absolute as classical general relativity indicates. Let's explore these theoretical escape hatches, these conceptual backdoors that hint at connections between black holes and other cosmic domains. We'll begin with perhaps the most famous speculative escape route: wormholes. A wormhole, or Einstein-Rosen bridge, is a hypothetical tunnel through space-time that could connect distant regions of the universe or even different universes entirely. In their simplest form, wormholes emerge naturally from the same equations that describe black holes. When Carl Schwarzschild solved Einstein's field equations for a spherically symmetric mass in 1916, his solution contained not just what we now call a black hole, but also a structure that mathematically resembles a tunnel to another region of space-time. This mathematical bridge was further developed by Einstein and Nathan Rosen in 1935, leading to the concept we now call an Einstein-Rosen bridge, or wormhole. In its original formulation, this wormhole isn't traversable. Any object attempting to pass through it would encounter the singularity and be destroyed. Additionally, the wormhole would collapse so quickly that nothing could pass through it before it pinched off. So while the mathematics suggests a connection to another region, it doesn't provide a practical escape route. However, in 1988, physicists Kip Thorne and Michael Morris showed that by introducing exotic matter with negative energy density, a wormhole could theoretically be held open and made traversable. This traversable wormhole would allow two-way passage without encountering a singularity. The catch: exotic matter with the required properties may not exist in nature. It would need to violate various energy conditions that all known forms of matter obey. Some quantum effects, like the Casimir effect, do involve negative energy densities, but it's not clear whether these effects could be harnessed to create macroscopic amounts of exotic matter sufficient to stabilize a wormhole. If traversable wormholes are possible, they would represent not just an escape route from black holes but a profound revision of our understanding of space-time. They would allow for apparent faster-than-light travel between distant regions, though without actually violating special relativity locally, and potentially even time travel, with all the causality paradoxes that entails. Recent developments in the study of quantum entanglement have provided new perspectives on wormholes. In 2013, Juan Maldacena and Leonard Susskind proposed the ER=EPR conjecture, suggesting that entangled quantum particles are connected by tiny wormholes. This would mean that quantum entanglement, Einstein's spooky action at a distance, and gravitational wormholes are different manifestations of the same underlying phenomenon. If true, this conjecture hints at deep connections between quantum mechanics and gravity that might eventually lead to a unified theory. It also suggests that the interior of a black hole might be more connected to the outside universe than classical general relativity indicates, connected through a complex web of quantum entanglements that could, in principle, allow information to escape. But even if wormholes exist, and connect black hole interiors to other regions, they wouldn't provide a practical escape for you once you've fallen in. The wormhole would likely connect to regions far from where you entered, possibly to distant parts of our universe or even to other universes entirely. Your component particles might eventually emerge elsewhere, but not in any form that preserves your consciousness or identity. Another speculative escape route involves the evaporation of black holes through Hawking radiation. As Stephen Hawking showed in 1974, quantum effects cause black holes to emit radiation and gradually lose mass. Eventually, after unimaginably long times, black holes should completely evaporate. For a stellar mass black hole, this evaporation would take roughly 10 to the power of 67 years, an almost incomprehensible time span, many orders of magnitude longer than the current age of the universe. But in principle, the information that fell into the black hole could emerge in the pattern of this radiation, albeit in an extremely scrambled form. The mechanism for this information release remains controversial. In Hawking's original calculation, the radiation was perfectly thermal, carrying no information about the black hole's contents. This led to the information paradox we discussed earlier. More recent work suggests that subtle quantum correlations in the radiation could encode all the information that fell into the black hole, preserving it in a highly transformed state. If this information preservation mechanism is correct, then when you fall into a black hole, the specific quantum state that constituted you isn't lost forever. It's gradually released in the Hawking radiation over billions upon billions of years. This doesn't constitute survival in any meaningful sense, but it does mean that the universe retains some record of your existence, encoded in the complex pattern of radiation emitted during the black hole's eventual demise. A third speculative escape involves bouncing black holes, where the collapse doesn't lead to a singularity but to a rebound or bounce. In these models, as matter reaches extreme densities, quantum gravitational effects create an outward pressure that counteracts gravity, causing the collapse to reverse. This bounce could lead to several outcomes. In some scenarios, it results in an explosion that releases the black hole's contents back into our universe. In others, it creates an expanding region on the other side that forms a new universe connected to ours only through the black hole. This latter possibility is sometimes called a baby universe or universe in a black hole scenario. If black holes do create baby universes, then your fall into a black hole might end not in destruction but in a transition to a newly forming cosmos. Your component particles would contribute to the matter content of this new universe, potentially becoming part of new structures, new forms, even new life over the vast spans of cosmic evolution. This scenario connects to speculative ideas about cosmic reproduction and natural selection at the universe level. If universes can give birth to other universes through black holes, and if the physical parameters of these child universes vary slightly from their parents, then a form of cosmic evolution could occur. Universes that produce many black holes would have many offspring, potentially leading to a multiverse dominated by universes finely tuned for black hole production. A fourth speculative escape route involves more exotic quantum effects, particularly quantum tunneling. In quantum mechanics, particles can tunnel through energy barriers that would be impassable according to classical physics. This tunneling has a non-zero probability even when classical escape is impossible. Applied to black holes, quantum tunneling suggests that particles inside the event horizon have a non-zero, though typically minuscule, probability of escaping to the outside. For microscopic particles, this probability is still extremely small. For macroscopic objects like humans, it's so vanishingly tiny as to be effectively zero, smaller than the probability of all the air in a room spontaneously gathering in one corner. But over the virtually infinite time spans that black holes exist, even extremely improbable events become relevant. Given enough time, quantum effects might allow the information content of the black hole to leak out through processes beyond classical description. A fifth speculative possibility involves black hole remnants, stable or long-lived objects that remain after a black hole evaporates. These remnants might store the information that fell into the black hole, preserving it until, well, until what? The theory doesn't specify, perhaps until some future cosmic epoch where conditions allow this information to be released or accessed. The existence of stable remnants would solve the information paradox by providing a repository for all the information that fell into the black hole. However, it creates other theoretical problems, particularly regarding the entropy and information capacity of such objects. A sixth speculative escape, perhaps the most exotic, involves backward causation, effects preceding their causes. Some interpretations of quantum mechanics, particularly the transactional interpretation and the two-state vector formalism, allow for influences moving backward in time under specific circumstances. Applied to black holes, these frameworks suggest that information about what falls into a black hole could influence the Hawking radiation emitted earlier, creating a channel for information escape that moves backward in time from our perspective. This would preserve information without violating the principles of quantum mechanics, though at the cost of challenging our intuitive understanding of causality. All these speculative escapes share a common theme. They suggest that the apparent finality of a black hole might be an artifact of our incomplete understanding rather than a fundamental feature of reality. They hint at connections, transitions, and information flows that transcend the simplistic picture of matter falling into a cosmic trap and being lost forever. But they also share another feature. None of them offer practical escape for you personally. Once you've crossed the event horizon, your conscious experience still ends with the destruction of your physical form by tidal forces. These theoretical escapes concern the fate of information, not the continuity of consciousness or identity. Even in the most optimistic scenarios, say your component particles seeding a new universe or your quantum information eventually emerging in Hawking radiation, what emerges is at best a highly transformed echo of what fell in. It's like arguing that burning a book preserves its information because the exact pattern of smoke, ash, and heat could theoretically be used to reconstruct the original text. This distinction between information preservation and practical survival highlights a gap between the concerns of theoretical physics and those of human existence. Physics cares about the ultimate fate of information. Humans care about the continuity of consciousness and experience. These speculative escapes may resolve the abstract information paradox, but they offer cold comfort to the falling observer. Nevertheless, these theoretical possibilities reveal something profound about black holes. They may not be the absolute end they appear to be. They may be transitions rather than terminations, transforms rather than deletions, gateways rather than graves. This perspective connects to ancient philosophical intuitions about the conservation of being, the idea that nothing truly disappears from the universe but merely changes form. Matter cannot be created or destroyed, states the first law of thermodynamics. Perhaps information follows a similar principle, persisting through transformations so extreme they blur the line between existence and non-existence. Recent developments in theoretical physics have strengthened some of these speculative ideas while weakening others. The discovery of gravitational waves from black hole mergers by LIGO in 2016 confirmed key predictions of general relativity regarding black holes but didn't directly address these more exotic possibilities. The first image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, showed a structure consistent with general relativity's predictions but again couldn't probe the exotic physics that might allow for these speculative escapes. Theoretical work on quantum gravity continues to evolve rapidly, with frameworks like string theory, loop quantum gravity, causal set theory, and asymptotic safety offering different perspectives on what might replace the classical singularity. Each of these approaches suggests different mechanisms for information preservation and potential escapes from the black hole interior. The holographic principle, particularly as developed in the ADS-CFT correspondence, suggests that the entire interior of a black hole can be encoded on its two-dimensional horizon. In this framework, information isn't truly inside the black hole in a conventional spatial sense, potentially offering a conceptual escape route for information, if not for physical objects. Quantum information theory has provided new tools for understanding how information might be preserved despite apparent loss. Concepts like quantum error correction suggest mechanisms by which information could be protected against the scrambling effects of falling into a black hole, emerging in Hawking radiation in a recoverable though highly encoded form. The field of quantum thermodynamics offers yet another perspective, suggesting that black holes represent states of maximum entropy for their mass and other parameters. In this view, falling into a black hole is an extreme form of thermalization, a transition from a highly ordered low-entropy state U to a high-entropy state where that order is distributed across the black hole's degrees of freedom. All these theoretical developments point to a common conclusion. Black holes are not the simple cosmic trash compactors they initially appeared to be. They're complex information processors that transform rather than destroy, that encode rather than erase. This transformation perspective offers a kind of cosmic consolation, though not personal salvation. When you fall into a black hole, you end your consciousness, your experience, your identity as an integrated system, capable of thought and feeling. But the information that constituted you persists in some form, contributing to the ongoing information content of the universe. In this sense, falling into a black hole resembles other natural transitions, like death and decomposition, but at a more fundamental level. Your component atoms will continue to exist after your death, becoming part of other structures and systems. Similarly, the information that constituted you continues to exist in some form after falling into a black hole, though transformed beyond recognition. This persistence without continuity raises profound philosophical questions about identity and existence. If all the information that constituted you still exists somewhere in the universe, encoded in Hawking radiation, transferred to a baby universe, preserved in quantum correlations, but cannot in principle be reassembled into a conscious you, has something fundamental been lost? Or is the continuity of information sufficient for a kind of cosmic immortality, even without the continuity of consciousness? These questions extend beyond physics into metaphysics, into our fundamental understanding of what it means to exist, to persist, to be. Black holes at the edge of our physical understanding naturally raise these edge cases in our philosophical frameworks as well. For now, these speculative escapes remain theoretical possibilities, not established facts. They represent potential resolutions to the puzzles posed by black holes, particularly the information paradox, which, if any of these possibilities turns out to be correct, depends on the still unknown correct theory of quantum gravity. Until that theory is developed and tested, black holes remain cosmic question marks, regions where our best theories fail, and where the true nature of space, time, matter, and information remains obscured. They stand at the edge of physics not just as challenges to our current understanding, but as guides to whatever deeper theory will eventually replace it. And for you, the hypothetical traveler on this one-way journey, these speculative escapes offer little practical comfort. Once you cross the event horizon, your fate as a conscious entity is sealed, regardless of the ultimate fate of your component information. The black hole represents an end, if not of your information, then certainly of you as you know yourself to be. This finality, this absolute transition from existence to non-existence, at least in conscious form, connects black holes to our deepest existential concerns, to our awareness of our own mortality and our quest for meaning in a universe that will eventually reclaim all that we are. The cosmic aftermath of your fall, the ultimate fate of the black hole itself and the universe that contains it, is the final chapter in this journey, a story that extends far beyond any individual existence into the deep future of the cosmos itself. We followed your hypothetical journey from the initial approach to a black hole, through the physical torments of spaghettification, the temporal distortions of extreme gravity, the inferno of the accretion disk, the visual paradoxes of the photon sphere, the one-way boundary of the event horizon, the quantum uncertainties of information theory, the breakdown of physics at the singularity, and the speculative possibilities for information escape. Now let's pull back, way back, to consider the cosmic aftermath of your fall. What happens to the black hole that consumed you? What is its ultimate fate? And what does your journey into oblivion mean in the grand context of cosmic evolution and the eventual fate of the universe itself? After consuming you, a negligible addition to its mass, the black hole continues its existence potentially for trillions upon trillions of years. If it's part of a binary system with a normal star, it may continue to feed on material from its companion, growing slowly over cosmic time. If it's isolated, it will grow only when chance encounters bring matter within its capture radius, an increasingly rare occurrence as the universe expands and the average density of matter decreases. But even in isolation, the black hole doesn't remain completely static. Quantum effects cause it to emit Hawking radiation, a slow leakage of energy that causes the black hole to lose mass over time. For a stellar mass black hole, this process is glacially slow. The temperature of the radiation is inversely proportional to the black hole's mass, making larger black holes colder and slower to evaporate. A black hole with the mass of our Sun has a temperature of only about 60 nanokelvin, billions of times colder than the current cosmic microwave background radiation that permeates the universe. This means it actually absorbs more radiation from the cosmic background than it emits, causing it to grow slightly rather than shrink. But the cosmic background radiation itself cools as the universe expands. In about 100 trillion years, when the cosmic background has cooled below the black hole's temperature, the net radiation flow reverses. The black hole begins to lose mass, evaporating with excruciating slowness at first, but with increasing rapidity as it shrinks. During this evaporation phase, the information that constituted your body, along with all other matter that fell into the black hole, potentially emerges encoded in the pattern of radiation. Not as recognizable matter, not in any form that preserves consciousness or identity, but as subtle correlations in the radiation that theoretically contain all the information about what fell in. For a stellar mass black hole, The complete evaporation process takes around 10 to the power of 67 years, a time span so vast that it dwarfs the current age of the universe by a factor of 10 to the power of 57. During this near eternity, the universe around the black hole changes dramatically. Star formation ceases after perhaps another trillion years, as the available gas is either converted to stars or dispersed too widely for gravitational collapse. The existing stars gradually exhaust their fuel. The most massive stars have long since exploded as supernovae, or collapsed into black holes of their own. The intermediate mass stars have evolved into white dwarfs. The smallest, most common stars, red dwarfs, continue shining dimly for up to 10 trillion years before they too fade to white dwarfs. These white dwarfs, the cooling corpses of stars, slowly radiate away their thermal energy. After around 100 trillion years, they cool to black dwarfs, dark cinders too cold to emit significant visible light. The universe enters the black dwarf era, a dark age where the only significant sources of energy are proton decay, occasional collisions between compact objects, and the slow evaporation of black holes. If protons do decay, still an open question in physics, then even the black dwarfs eventually dissolve, their constituent matter converting to radiation over timescales of 10 to the power of 37 years. The universe becomes increasingly diffuse, populated primarily by black holes, neutrinos, photons, and other elementary particles, all separating from each other as cosmic expansion continues. Throughout these vast epochs, the black hole that consumed you continues its slow evaporation. As it loses mass, its temperature increases, causing it to radiate more rapidly. The final stages of evaporation occur with a sudden acceleration. In the last second of its life, when the black hole has shrunk to subatomic size and reached temperatures of billions of degrees, it releases an explosive burst of high-energy radiation, a tiny echo of the Big Bang that created the universe. And with that final burst, the black hole is gone. Nothing remains of the entity that consumed you except the radiation it emitted during its lifetime. Radiation that spreads outward into an increasingly empty universe, its energy eternally diluted by cosmic expansion. This eventual dissolution of black holes represents the final dispersal of concentrated matter in the universe. Once the last black hole evaporates, after timescales of 10 to the power of 100 years, the universe contains no structures larger than elementary particles, no concentrations of matter, no gradient of energy from which work can be extracted. This state, the heat death of the universe, represents maximum entropy, the complete exhaustion of all potential for change or organization. No new stars can form, no biological processes can operate, no computation can occur. The universe becomes a nearly perfect vacuum, populated only by extremely diffuse radiation and elementary particles, all expanding away from each other forever. In this final state, the atoms that once constituted your body, the information that once constituted your mind, along with all other matter and information that ever existed, has been converted to radiation and dispersed throughout an effectively infinite volume. The universe approaches a state of perfect homogeneity, perfect equilibrium, perfect stillness. This cosmic heat death is the ultimate expression of the second law of thermodynamics, the principle that entropy disorder always increases in closed systems. The universe as a whole is the ultimate closed system. Its journey from the highly ordered low-entropy state of the Big Bang to the maximally disordered state of heat death represents the largest possible increase in entropy that can occur. Your fall into a black hole, viewed in this cosmic context, represents a small step in this universal journey toward maximum entropy. The highly ordered arrangement of atoms that constituted your body is transformed into radiation, contributing to the universe's gradual progression toward disorder and equilibrium. This may seem an unutterably bleak picture, a universe winding down to eternal emptiness, all traces of life and mind eventually erased, all forms and structures dissolved into formless radiation. But there are several speculative possibilities that might modify this scenario. One possibility involves vacuum decay. Our current understanding of particle physics suggests that the vacuum state of our universe, what we consider empty space, might not be the lowest possible energy state. If a lower state exists, our universe could potentially transition to it through a process called vacuum decay, where a bubble of true vacuum nucleates somewhere and expands at the speed of light, transforming everything it touches. This transition would release enormous energy, potentially creating conditions similar to the early universe, and allowing new structures to form. From our perspective, such a transition would be instantaneously destructive, a cosmic reset button that erases the existing universe. But it would represent a kind of rebirth for the cosmos as a whole, a new beginning rather than a final end. Another possibility involves random quantum fluctuations over unimaginably long timescales. Given enough time, far longer than the timescales we've discussed so far, random quantum fluctuations could potentially produce organized structures, even conscious entities, through pure chance. These Boltzmann brains or other fluctuation-born structures would be vanishingly rare and temporary, but in an eternal universe, even the most improbable events eventually occur. A third possibility involves new physics at scales, or in conditions we haven't yet been able to test. Our current understanding of the universe's long-term evolution is based on extrapolating known physics to extreme timescales. If our current theories are incomplete, as they almost certainly are, the actual fate of the universe might differ from these projections. But regardless of these speculative alternatives, the universe as we know it, the universe of stars and galaxies, planets and living things, structure and organization, will eventually end. The black holes that now populate the cosmos, including the one that hypothetically consumed you, represent way stations on this cosmic journey, temporary repositories of matter and energy that delay but cannot prevent the ultimate dispersal of all things. This cosmic mortality, this ultimate impermanence, raises profound questions about meaning and purpose in the universe. If all structures eventually dissolve, all information eventually disperses, all complexity eventually simplifies, what significance can we attribute to the temporary forms and patterns that exist now? Different philosophical traditions offer different answers to this question. Some suggest that meaning lies precisely in the temporary nature of existence, that it's the transience of patterns that gives them their value. Others propose that subjective meaning created by conscious entities needs no cosmic permanence to be genuinely significant. Still others find meaning in the idea that while specific forms may dissolve, the fundamental substance of existence persists eternally, merely changing shape rather than disappearing entirely. Your hypothetical fall into a black hole serves as a microcosm of this larger cosmic journey. The specific arrangement of matter and energy that constituted you dissolves, but the fundamental constituents persist in transformed states. Your information is not destroyed but redistributed, not erased but encoded differently. In this sense, falling into a black hole is less a destruction than a transformation, an extreme version of the transitions that all matter undergoes in the cosmic cycle. Stars form from gas clouds, shine by nuclear fusion, exhaust their fuel and expire as white dwarfs, neutron stars or black holes. Planets coalesce from debris disks, evolve through geological processes, and eventually dissolve as their parent stars expand or die. Living organisms emerge from simple chemicals, develop through natural selection, and eventually return their constituent elements to the environment. Your fall into a black hole represents an acceleration of this universal rhythm, a compression of the normal cycle of transformation into a brief but extreme event. The atoms that formed your body return to the cosmic inventory, eventually to be released in the black hole's final evaporation, and to continue their journey through an evolving universe. This perspective doesn't negate the horror or finality of the experience from your subjective viewpoint. Consciousness ends. Identity dissolves, the specific nexus of matter, energy and information that constituted you ceases to exist as an integrated functioning system. But it does connect your individual fate to the larger cosmic story, a story of continuous transformation rather than absolute endings. In the deepest sense, black holes embody the dual nature of cosmic processes. They represent both destruction and conservation, both endings and transitions, both increase in entropy and preservation of information. They are cosmic catalysts that accelerate the universe's evolution toward its final state, while potentially encoding all they consume in forms that could theoretically persist until the end of time. Your hypothetical journey into a black hole thus serves as a lens through which to examine our place in the cosmic cycle, our temporary existence as organized systems, our inevitable dissolution, and the uncertain fate of the information that defines us. It compresses cosmic timescales into a single catastrophic event, making visceral and immediate processes that normally unfold over billions of years. And perhaps that's the true value of this thought experiment. Not as a practical guide to black hole survival, there is none, but as a concentrated metaphor for our cosmic situation. We exist temporarily as organized systems in a universe that permits such organization for limited periods, but eventually reclaims all structure into simpler forms. Our consciousness, our identity, our sense of self all depend on specific arrangements of matter and energy that cannot persist indefinitely. Black holes make this temporary nature of organization explicit and extreme. They strip away the illusion of permanence that our relatively stable terrestrial environment creates. They remind us that even the most durable structures in the universe, planets, stars, galaxies, are ultimately transient patterns in a cosmos that will eventually dissolve all forms back into the void from which they emerged. This reminder of cosmic impermanence can be seen as either profoundly disturbing or strangely liberating. It challenges us to find meaning not in eternal persistence but in temporary existence, in the brief local decreases in entropy that allow complex structures like stars, planets, living organisms, and conscious minds to exist for a time before returning to simpler states. In this view, meaning emerges not despite but because of impermanence. The fact that ordered systems can exist at all in a universe governed by the second law of thermodynamics becomes a kind of miracle, a temporary rebellion against the cosmic tide of increasing entropy. Our existence as conscious structured beings represents a brief but magnificent moment when the universe becomes aware of itself, when matter organizes into forms capable of contemplating their own nature and fate. Black holes, as the most extreme engines of transformation in the cosmos, highlight this transient nature of organization. They are the ultimate expression of the universe's tendency to return complexity to simplicity, structure to randomness, order to chaos. But they also, through their preservation of information in radiation, hint at a more subtle conservation, a preservation not of form but of essence, not of structure but of the underlying reality that temporarily adopts these structures. And so your hypothetical fall into a black hole, terrible as it would be from a personal perspective, connects to the grandest themes of cosmic evolution, the emergence of complexity from simplicity, the temporary existence of ordered systems in a universe tending toward disorder, and the ultimate return of all structures to the simplicity from which they arose. In falling into a black hole, you would experience in minutes what the universe as a whole will experience over trillions of years: the dissolution of structure, the dispersal of information, the transition from organization to entropy. Your individual story would merge with the cosmic story, your personal ending becoming a microcosm of the universe's own journey toward its final state. And perhaps there's a kind of cosmic comfort in this connection, in knowing that even in the most extreme fate imaginable, you remain part of the universal process, your constituent elements continuing their journey through an evolving cosmos, your information preserved in subtle forms that persist until the end of time itself. For in the final analysis, black holes don't represent absolute endings but transitions, extreme, irreversible, transformative transitions that change the state of matter and energy without eliminating their fundamental reality. They are cosmic processes, not cosmic terminators, engines of transformation that reshape rather than destroy, that encode rather than erase. And in this capacity, they serve as the ultimate teachers about our place in the cosmos, reminding us of both our impermanence as specific forms and our persistence as part of the fundamental substance of existence. They embody the cosmic rhythm of emergence and dissolution, complexity and simplicity, organization and entropy, that defines the universe's evolution from its beginning to its end. Your journey into a black hole would be the most extreme expression of this rhythm, the fastest, most violent transition from complexity to simplicity possible in nature. But it would not represent a departure from the cosmic process but rather its intensification, a compression of universal patterns into a singular event that makes explicit what is usually hidden by the vast timescales of cosmic evolution. And so, as we conclude this documentary journey through the physics of falling into a black hole, we're left not just with horror at the fate described but with wonder at what it reveals about our universe, a cosmos that permits temporary organization without permanent structure, temporary complexity without eternal form, temporary consciousness without immortal mind. Black holes stand at the edge of our understanding, regions where our best theories fail, and where the deepest questions about space, time, matter, and information remain unresolved. They challenge us to recognize both the limits of our current knowledge and the extraordinary progress we've made in comprehending the cosmos. And in their ultimate fate, their eventual evaporation into radiation, their return of all they've consumed to the cosmic inventory, they remind us that nothing in the universe truly ends. It merely changes form, transforms state, transitions from one configuration to another in the grand cosmic dance that began with the Big Bang, and will continue until the final dissolution of all structure. Your hypothetical fall into a black hole would be a small step in this cosmic journey, a transfer of matter and energy from one form to another, a redistribution rather than a destruction. And in this perspective, perhaps we find not comfort exactly, but a kind of cosmic belonging, a recognition that even in the most extreme fate imaginable, we remain part of the universe's story, participants in its evolution, contributors to its eventual state. For we are, all of us, temporary patterns in a cosmos that permit such patterns for a time before reclaiming them. Black holes simply make this fundamental truth explicit, compressing the normal cycle of transformation into a single catastrophic event that strips away illusions of permanence and reveals the transient nature of all structures, all forms, all organized systems. And in that revelation lies both a profound challenge to find meaning in impermanence and a possible path to such meaning, a recognition that value lies not in eternal persistence but in temporary existence, not in forever but in now, not in immortality, but in the brief, magnificent opportunity to be a conscious part of a universe capable of knowing itself.